Good morning. Welcome to day one of the third and final Alaska Sustainable Energy Conference pre-event workshop for 2024. My name is Brittany Smart, and I'm the Energy Transitions Initiative Coordinator at the Alaska Center for Energy and Power, which is the primary sponsor of this workshop series. I'll be your MC today, and thank you so much for joining us once again. This is the third in a series of 3 virtual workshops. They have been held monthly as 2 half-day Zoom sessions, free of charge, leading up to the Alaska Sustainable Energy Conference, which is taking place in person from May 20th to the 23rd at the Denina Center in Anchorage, Alaska. The purpose of these workshops is to take a deeper dive into specific topics that are of current relevance to the energy opportunity and challenges facing Alaska today. This is the 3rd year that ACEP has hosted these workshops. We bring some of the top experts and practitioners together to share information and their perspectives on issues that are of interest as we work towards Alaska's energy future. All of the workshops are recorded, and you can find them on the Alaska Sustainable Energy Conference website. Previous topics have included nuclear energy in Alaska, ocean and river energy, hydrogen, low carbon energy transitions, carbon capture and sequestration, and energy storage. We have posted the link in chat in case you'd like to revisit any of those topics. For this year's workshops, we took a different approach. Rather than focusing on the different technologies, we look at the broader picture of our energy system. Last month, we focused on transmission and distribution, the clean energy transition secret weapon. We heard from different perspectives and approaches regarding how our energy transmission and distribution systems are critical aspects of energy infrastructure and are essential for driving sustainable change in Alaska's energy future. For this workshop, we are looking to the future, and we are focused on betting big, investing in emerging energy technology. We also hope you'll join us in a few weeks for the 2024 Alaska Sustainable Energy Conference. So let's get right into it. This morning, we will start by hearing from the University of Washington students on efficient energy research, building an advanced language model and interface. Next, we'll dive into the role of AI, opportunities and considerations, where we will have a facilitated discussion with Leslie Canavera with Pole Arctic, Richard Lum with Vision Foresight Strategy, and Clay Copland with Cordova Electric Association. After that, we will hear from Jay Byam, the CEO of Cartorium, to provide a presentation on digital twins, where to start. We will close out day one with a case study on H2 deployments and blending by Laurent Nassif from the Alaska Center for Energy and Power. Tomorrow morning, the conversation continues as we learn more about the Kafla Magma Testbed, a vision for advancing geoscience by John Eichelberger from the Alaska Center for Energy and Power. Alaska Governor Mike Dunleavy will then join us to provide live remarks. Next, we will continue with a panel discussion around the rural Alaska experience, innovation versus emerging tech. We will be joined by Katie Conway from the Denali Commission, Brian Hirsch from Deerstone Consulting, Taniqua Hay from the Department of Energy, and Dave Messier from the Tanana Chiefs Conference. We'll conclude the workshop with a panel discussion, grid-forming inverters in the real world. Before we get started, let's take a look where all of our attendees are joining us from today. To participate in today's polls from your computer, please go to pollev.com/TOTTAK216. We recommend using Google Chrome for the best results. The link to the poll is also in the chat. To participate by phone, please text TOTTAK216 to the number 22333. You will receive a text message once you've joined the session. Type and send your response, and the results will pop up on the next screen. Can we please have the map pulled up on the screen? First, we'd like to know, where are you joining us from? You can just drop a pin in the map or circle from where you're from. Let's give it a minute to see who we've got coming in. We've got some Anchorage folks joining us. At least another one down there. Looks like that's the concentration of activity today. A couple from outside the state. Excellent. And one outside the country. couple coming in from, at least one from Fairbanks, a few more from Anchorage. All right, we'll give it another second here. All right, I'm not seeing any more pins pop up. Thank you for sharing where you're joining us from today. For our second question, we're interested in knowing, what is your overall sentiment towards AI technology? Is it optimistic, skeptical, or neutral? We'll give it a few moments for people to submit their answers. Oh, it looks like we're kind of split there in optical and skeptical. And while those answers are coming in, you may find it interesting that we actually asked for the assistance of AI to help us develop this question. So I thought that was fun. All right, we've got some pretty solid splits there. Half of the people are optimal, half are skeptical, and just a couple who are neutral. Thank you so much for providing your input there. Now we'll move into some housekeeping items. Please introduce yourself in the chat. Let us know your name and the organization you're joining us from. If you're having any difficulties with audio or trouble viewing the presentation, please send a chat message to event support for assistance. During the workshop, all attendees will be muted. Please submit any questions you may have in the chat. Our moderators will collect and curate those questions to be used during the Q&A portion of each section. The recording of this workshop will be available on the ACEP website at www.alaskasustainableenergy.com. Please continue to check back for more information. But we are glad you're live with us here today. Starting us off this morning, my apologies. As a reminder, again, please put any questions in the webinar chat and we will get to those in the Q&A portion. Now, please join me in welcoming Daha Nur from the Alaska Center for Energy and Power. He's been working with students from the University of Washington and will moderate our first presentation for today, Efficient Energy Research, Building an Advanced Language Model and Interface. Daha, thank you so much for joining us. Please take a quick moment to introduce yourself and your team, and the floor is all yours.
Thank you, Brittany. Hi, everyone. My name is Daha Noor. I'm a DevOps engineer and data scientist with the University of Fairbanks ACEP data management team. In conjunction with the University of Washington College of Engineering Industry Capstone program, we've been piloting how advanced language models and chat interfaces can support researchers with efficient energy research. Essentially, the Industry Capstone program brings together UW students and professionals to tackle engineering problems, and ACEP provides support to students who are designing and building innovative solutions. So I'll go ahead and hand over the mic to the Capstone team to introduce themselves, and we'll get started on the presentation.
Hi, my name's Kashetty.
I'm Aaron Hong.
I'm Nishir Nakata.
I'm Najib Haida.
And I'm Whitney Waldinger.
And for our capstone project, we partnered with the Alaska Center for Energy and Power. Our industry mentor is Daha Nur. Our faculty mentor is Rajesh Subramanian. And we'll be presenting our project of building an LLM, a large language model for energy research papers.
So why an LLM? Well, you see, we're all students and we have had industry experience and we know what it's like to work in the industry. We know that things need to be done fast and efficiently, done well. The best way to get up to pace on any type of subject is to ask your knowledgeable friend or ask your friend who's been in much experience more than you and has been around more. Well, what if we could bring that friend to you? What if there was some chatbot that you could just talk to, discuss? And when you want to have information about doing some type of research, you could just consult that chatbot and it would bring the information to you. This would save so much time because it's so time consuming to find relevant documents on any type of research you're trying to do. So what if we could bring the documents to you, and what if we could just source them so that you can look through those documents after they've come to you and you can find out more information if that document is relevant to your research. So what's our goal here? You see, this is a picture from Perplexity AI. The way Perplexity AI works is that you ask it a question, it gives you an answer, and then the source is from where it got the answer. What's the difference between what we're doing and what Perplexity does? You see, Perplexity searches the internet. Perplexity tries to find relevant sources to your query from the internet publicly. But what if you want to work on it internally? What if you want to have your own documents on there? What if you want to focus on more scholarly documents? That's what our LLM is going to do. Our LLM is going to enable you to ask it a query about a certain research topic, and it'll be able to give you back on those sources all the relevant sources that you would need to find more information about your topic, cutting the time from doing research down significantly. And so not only do we want to make this happen, but we also want to make it open source so that everyone can use it, and also very modular so people can use it in their own way. Within a month, we should have our GitHub fully up to date, and you can just pull the repo and customize it for yourself, your own information, your own bot.
Yeah, so to give you guys a quick overview of how our project data pipeline works, basically you start off with PDF documents that will eventually become a large language model chatbot that you can interact with on a website. So to guide you through the pipeline, we start off with the PDFs. Those are fed into an OCR module, an optical character recognition model. That basically pulls out all of the text from the PDF, and then it creates JSON formats, which are just text-rich formats that like a machine can interpret. Those are then fed into a vector database, which converts it to a numerical format that the LLM can then use to understand all of those documents. With the LLM and the vector database linked, the last step you need is just a way to interact with it. We use Flask as our intermediary, which just allows you to send queries back through Flask to interact with the LLM, which could then formulate a response using all of the information in the vector database, and then send that response back through Flask to the website for you to read. And then now on to a more in-depth view of the back end. We start off, of course, with the PDFs, and those are, of course, fed into the OCR model. In this case, we're using Tesseract for our OCR. Those then spit out the JSON files, which Najib will now cover.
Yeah, thank you, Ichiro. So after we grab those documents and pass them to our OCR is basically looking to extract text. But sometimes we have too much text to extract at once that our LLM can't process it all at the same time. That's why we rely on something called a chunker. The chunker is basically going to take like a couple sentences away from each document and split it up into its own JSON document. And so we'll have an image right now about JSON documents and the way they look like, but JSON is basically going to allow us to basically separate that chunk into the meaningful information. So some extra metadata. As you can notice, there's some key value pairs, for example, like text. Text is like the text inside that specific chunk. We have other information, for example, our embeddings at the bottom. So at the bottom, you'll see that embedding, that vector. That embedding is what's being stored inside the vector database. So we're transforming this set of words into a vector of numbers so that our computer can understand it better and be able to compare to the query. Move on, please, Ichiro. So as you can see, we pass those chunks or those JSONs into the vector database. So we're having those vectors inside the vector database. And then once we have those vectors inside the database, once the LLM receives some type of query, like you're trying to ask it a question, it's going to be able to use some techniques such as cosine similarity to compare those two vectors and find out how similar they actually are. After it does so, it can just bring you to the forefront the most relevant documents inside your database, and then your LLM can then look through that text, look through that metadata, and give you back the optimal answer to what you're looking for, while also citing which documents were brought to the surface. I'm going to pass it on to Aaron to show us how we can connect this to the front end.
Thank you, Najib. The last part of the backend is Flask. Flask is a powerful Python framework which has the capability to connect our database and large language model to the website via internet traffic. As Najib said, information is sent back to the vector database to be vectorized, and similar documents can be sent back over Flask to the website. On the next slide, if you could, Ichiro, we talk about some of the design choices that we made. A lot of the design choices that we made were motivated by a desire for modularity and usability for developers, and for our code to be reusable in the future. In terms of hosting the live service part of our code, which is the Flask app, we decided to go with Google Cloud Run because it's serverless and we only need to pay for what we use. But that's only one of many places where it could be hosted. Developers in the future could use the code from the GitHub to either host it on Google Cloud Run like we did, or host on a local machine, or even a virtual machine, which is something that we considered, or even something like Cloudflare. The PDF processing pipeline, which allows us to ingest new documents into the database, is also going to be available on our GitHub as a Python script, which developers can also utilize for their own needs. I'll pass it over to Akash to talk more about the design choices.
Yeah, so some of the other design choices that we made on the back end, right now we're using Together AI. Together AI allows us to use a Python library to access our large language model and our embedding model. The large language model that we're using right now is Llama 3. Llama 3 is a new open source model by Meta, one of the best on the market currently. It's also cheaper because it's open source, and there's a lot of documentation because it is also open source. We're also using Together AI along with MongoDB, our database, because they are easily integratable. MongoDB is our database that allows us to store our JSON files as well as our embedding vectors. And now I'm going to talk more about our implementation on our front end. So this right here is a early design for our chatbot, one of our research assistant, as you can see at the top. So at the bottom, you type the query, it goes to Flask, and then it goes to the large language model to be processed, and it is compared to our vector database to provide a response. And I'm going to give it over to Whitney to talk more about our front end.
Awesome. Thank you, Akash. So our front-end implementation is centered around React.js, which is a powerful JavaScript library used to create user interfaces. React.js provides us with a strong foundation for creating reusable UI components. So circling back to our overall project goal of creating an open source project, this allows for future developers to recycle and adapt our project to fit their specific use cases. And then leveraging React.js, we've structured our web page using predominantly TypeScript files as well as CSS files. And we already mentioned that we're using a Flask app to handle requests between the front end and the back end. In terms of the front end, we've utilized Axios, which is a popular HTTP client for JavaScript that allows us to have reliable and efficient means of handling these asynchronous requests. And then the deployment of our front-end application is managed through Cloudflare Pages, which is a platform that's tailored for hosting static websites, which is exactly what we have. Cloudflare Pages offers seamless integration with GitHub, which allows for automatic deployments every time a commit is made. And so this just ensures that our front end will be up to date with the latest changes to our repository. And then moving on to the design choices for front end. Throughout the front end process, we've utilized or focused on usability, interactivity, and user engagement when making decisions about what technology to use. We've opted for a chatbot interface rather than your typical search engine like Google or even Google Scholar because it provides a more intuitive and personalized user experience. As Najib mentioned, we really want to focus on just giving the user or researcher the information that they need. And so this just facilitates a better understanding of the user's needs and preferences. And then lastly, we decided to use Cloudflare Pages for deployment because of its simplicity, affordability, custom domain configuration, which will be super important for accessibility, and then also built-in performance monitoring. And this just ensures that our front-end application is accessible and performs optimally for users across different devices and different platforms. And Cloudflare has also emphasized their commitment to energy efficiency and sustainability, which is awesome as we create technology for the future. And now I'm going to pass it off so that we can demonstrate our chatbot in action.
Okay, and here's a little demo for you guys. This was filmed at the end of winter quarter. We've got 2 test documents in this. So just to play that right now, let me full screen it. You can see our chatbot interface right here. We've got the introduction here. You can, little chat bar at the bottom, you can send in the query. After that sends in, you can see it responds with exactly the source documents right there. There's another query we're going to type in here. It's going to show you a little bit more of an in-depth example and response that you could get. So right here, you can see all of the test documents right there. You click on it, and it guides you to the exact PDF that it drew the information from. That allows you to go more in depth on the topic, research all of it, and make sure it's all up to snuff. Okay. And then that's pretty much our demo. Moving along, we have our reference documents all right here. The link's right there. It's basically just a quick overview of everything we used in our build up to now. And are there any questions?
Awesome. Thank you all so much. I'll kind of moderate. If folks have questions, would love to get some of those maybe in the chat. Could really be about anything from the experience of, the program to maybe some concerns around AI and large language models, and so on and so forth. But, as folks maybe type in their questions in the chat, I can maybe start off with one, and then we can, I'll kind of moderate from there. I think this tool is really neat. I'm a big fan, of course. Post project, I know you all kind of mentioned there's going to be a repo. Can you all just kind of expand on that and share how folks can get their hands on it, and how maybe they can reproduce this in their own lab?
I guess there's a few questions coming in. Let's see. Will there be any efforts to assemble PDF source libraries of Alaskan energy documents to then be used with your product? So the idea is that basically we're going to be sending out all of the database tools that we used, so you could make your own database, but we are going to make an Acer dataset for the end project for this. We're currently incorporating the Acer dataset just for testing, but we'll have some sort of database by the end of this.
And ICER is the Institute of Social and Economic Research at ACEP. And so we've used their data set currently, as well as we have plans on using the regulatory RCA, the Regulatory Commission of Alaska as well. They produce a lot of research products around energy as well. There's another question. Is there a strategy for updating the LLM data and incorporating feedback? And I'm assuming feedback from end users. I can take that. Yes, I think there's a data pipeline, which means that constantly data could be fed into this model, and taking feedback from users, absolutely, in terms of whether these responses are positive or negative, or if the model, kind of needs to be guided. We've tested out fine-tuning as well as prompting as well. And so there's definitely a lot of expansion that we can do. Here's another question. Maybe I'll hand this one off to the team. Are there any efforts towards including HTML documents from websites, as well as PDFs from websites? This is from Alan Mitchell. Or is there the possibility of doing that, I guess?
Yeah, I can take that question. So definitely there is that possibility. We actually have a couple HTML documents in there. So the parser that we're using, or like the OCR, does have capability to parse HTML documents as well. So it'll be the same process, just instead of adding a PDF, you just add an HTML and you still get that JSON format that you can then query and add to your database.
Awesome. There's some questions around privacy and accuracy that I've noticed in the chat. What kind of privacy considerations went into our choice of our large language model? And then another question around, hallucination, right? There's very little relationship between these models understanding reality, and not, coming up and, making up stuff along the way. For the first part around privacy, we've been pretty adamant about choosing open source, and so that way it's reproducible. Other folks can kind of look under the hood and see exactly what's happening and what's going on. And all of the data that we're using is publicly available data. And so it's already available to everybody. And then around the hallucination, to Dan Tucker's point, Yeah, it's so far it's pretty accurate in terms of being able to find the specific source. And so the tool is really meant to help expedite researchers that are searching for specific content. There are capabilities around summarizing specific content that has different levels of efficacy, but in large part, being able to pinpoint where a specific word or a specific concept is within a document has proven to be pretty accurate. And then allowing researchers then at that point to take over and start, driving themselves and steer it themselves from there. This is a cool question from Rami Wood. Would some sort of incubator be helpful to explore where this work continues to go? Do you have any suggestions for possible public or private partnerships supporting such work moving forward? Do you folks want to maybe touch on it being open source and how other folks can collaborate, or what you all kind of see moving forward from here?
I mean, yeah, since our like project is going to be open source and on GitHub, that means that like anybody will be able to work with it, and anybody will be able to change our code to whatever they fit and use their own databases. So I feel like that's a lot of how the development of our project will go. And yeah.
Absolutely. And long term, ACEP will continue to, incubate this, and hopefully next year we'll get another group of really awesome students that can continue to kind of work on this. There's a cool question around, is there the ability to capture the base data in a different vector database? And I think maybe they're referring to the embeddings themselves. So does somebody want to maybe touch on the portability around the database and how to maybe reproduce the results that we got to?
I guess I can touch on that a little bit. So if you recall like the graphic that we used to segment the model, we kind of designed this with modularity in mind so that you can swap out a bunch of different components. Over the course of this project, we've swapped out a number of vector databases and different LLMs. So the idea is that once you get your hands on it, you can pretty easily swap out all the different modules there. So if you wanted to use something else, you can use a different data set, use a different vector database, maybe even a different processing OCR model, and just basically make it your own.
And yeah, that kind of ties back to the whole hallucination thing, is that as LLMs get better, them on their own will tend to hallucinate less, and you'll just be able to plug and play it directly into our system.
Yeah, the cool thing is that you're also going to be able to choose your LLM as well. So if, for example, Llama 3 is not something you enjoy and you'd rather use like GPT or Mixtral, you can easily make that change yourself. And that's the cool thing because the skeleton is all there. So you just need to plug and play with whatever compute you'd like.
Awesome. Do you all want to maybe touch on some of the technical challenges that you've encountered, maybe related to infrastructure, hosting, model deployment, as well as like any significant pivots you all have had to take to kind of address those challenges?
I mean, I guess going into this project, none of us really knew exactly what we were supposed to use. So it was a lot of exploring and just trying a bunch of different stuff. So a lot of interesting trial and error there, for sure. But I guess let's see, what are some of the bigger pivots? Probably, I guess shifting around the data pipeline would be, we've had a lot of shifts there. Najib, do you want to touch on that maybe a little bit more?
Yeah, we did try a lot of different methods, different techniques. Money was also a thing that like we didn't want to put too much money in something that we knew we weren't going to use maybe, and just a lot of testing, a lot of free trials, a lot of that kind of stuff, trying to work stuff out. I would say something also was just using so much data. So, for example, like creating a web scraper that's able to parse out all those PDFs from the ICER data set That took a long time for just to be able to pull and download all those PDFs just to feed our LLM or feed our database to try to see how well it's functioning. And then also after actually pulling out that data to pass it through the chunker to get to embed it all, that also took a lot of time. We had to like increase our MongoDB cluster, use different clusters, use different storage sizes, and just a lot of shifting around, a lot of playing around. But I think that's a strong testament as to how powerful this project actually is because, I mean, if when we're developing it, you can shift around so much, just imagine like the final product, how much you can shift stuff around as well.
That's a really cool question from Clay Coplin. I'll just read it out. It's a little bit longer. There are many obscure innovations in Alaska, some of which are game-changing, if you're aware of them. Could this database host a searchable library that could lead to legacy solutions like using a car battery and jumper cables to pinpoint a fault in a 138,000 volt submarine transmission line, like electrical engineers did in the 70s to find a break in the submarine transmission lines from Beluga gas plant across Cook Inlet to Anchorage. That is very, very specific. And I mean, I'd love to give that a go. But yeah, does somebody want to kind of touch on that and maybe, go over semantic search and how this really does solve for searching across legacy data sets like RCA and ICER that aren't as accessible or friendly?
I mean, yeah, absolutely. I would say for obscure innovations like the one you are talking about, Clay, and older records that are not so accessible on the internet and are only available as scans, a tool like this would be really good at um, making the data contained in these old scans more tangible for modern day users to work with.
Absolutely. Yeah. And that's one of the challenges that we had to overcome. Some of the files, to your point, date back to the 70s. And those PDFs are images and you kind of have to put them through a different processing pipeline to extract that information before it becomes available for search. And so there is a lot of pre-processing work that does take place. So yes, there's a lot of legacy data sets out there. Some of them need a little bit more love than others, and sometimes you got to prime the data just to make it ready. But for the most part, the end goal is to use the chat interface as the search tool itself, rather than a search bar that maybe just might pop up a single document. Now you can search across thousands of data sources and hundreds of thousands of documents, and be able to find, to your point, a very niche use case that happened in a specific document. And maybe this could be as a close. What lessons did you all kind of learn that I know, Ichiro, you kind of touched on the fact that there was a lot of learning that took place for this project. Maybe you all can just, touch on your experience prior to the project. Were these tools and frameworks that you all already knew? Were these skill sets that you already had? Or, are these new skill sets that you've picked up? And if so, how do you feel, all the things that you've learned will kind of help propel your career path in the future? And has it helped you kind of set you up for a future career decision that you may not have thought was possible prior to this project?
I mean, I guess just knowing that you can learn all of this stuff even in just a few months is kind of neat, especially since a lot of us kind of started not necessarily from scratch, but mostly from theory and not necessarily applied work from our classes. So just seeing all of the tools out there and how easy it is to get into once you start digging, it was kind of a eye-opening experience. And as for, I guess, informed career decisions, it's kind of pointed out that you can do a lot of this stuff yourself if you wanted to, and if you have not necessarily the know-how, you can get the know-how, but just the can-do attitude, honestly.
Yeah, Chiro, you made some great points. I just want to add on to that. I think something that's very valuable that we also gained from this experience was I don't think any of us have ever worked on a project this big before. And so we really learned the value of teamwork. So being able to split up our team into different subsections, each person working on something, having a deadline ready, and then just combine stuff and build off of each other as we go on. I think that's a really valuable experience that not a lot of us were exposed to since, our schoolwork labs were like 2, 3 students max. Whereas here we had 8. Unfortunately, 3 couldn't join today, but it was a great experience, definitely.
Absolutely. And I'd probably add to that, there's also 2 universities collaborating for this project as well. And so, there's much larger collaboration. There's administrators that are involved, mentors that are involved to kind of see this, project to fruition. And so it is very collaborative in nature. There are a lot of moving parts to kind of, see something of this size, in such a very short amount of time to be able to launch that, I think, kudos to you all for sure. And for you all, what, aspects of the project's like scope and mission really excited you all the most? Coming into it, the title kind of is, building LLMs for energy researchers, but, tying that back to what we do at ACEP has always been like, our North Star with this project, and hopefully making researchers' lives that much easier to go do the, amazing work that they do. And so with that framework of collaboration and, teamwork, how have you all been tying your work to kind of the broader goal of helping ACEP's researchers?
I think for me coming into the project, I hadn't had a lot of experience with LLMs, and so that's what excited me initially. And then I've always wanted to work on something that's obviously having such a huge impact, and in the field of energy, but in so many different fields where our project can now be used. We really can be like such a good resource and optimize, I guess, like the future of research for them, which was awesome. And I think being able to create something that is the future of technology and is going to be used in so many different industries for so many different reasons, I think it's just like, I don't know, I'm proud to be a part of it.
Absolutely. And are you all electrical engineer majors, or do you all have different majors as well?
We're all electrical and computer engineers.
Mm-hmm.
Awesome. Okay, I think we'll hand the mic back over to Brittany from here. Thank you all for the presentation, and thank you to Brittany for putting this together for us.
Great. Thank you so much to all of you for not only the presenting today, but the work that you're doing. One thing that ACEP is very proud of as an applied research institute is the role that we get to play to bring up the next generation of the workforce. And the work that you all are doing is super exciting. And we look forward to this project as you move forward. So thank you so much. Really appreciate you all. Next, we're going to be moving into a facilitated conversation. It's the role of AI, opportunities and considerations. I will be joined by Ms. Leslie Canavera, the CEO of Pole Arctic, Richard Lum, CEO of Vision Foresight Strategy, and Clay Coplin, CEO of Cordova Electric Cooperative. Thank you all so much for joining me today, and I couldn't think of a better way to set the foundation of our conversation than to hearing from those capstone students just now. First, I'm going to start with you, Leslie. Can you get us started by taking a quick moment to tell us a little bit more about yourself and Pole Arctic?
Sure. Thanks for having me. I'm the co-founder and CEO of Pole Arctic. I was born and raised in Alaska. I'm Yupik Alaska Native. Joined the Air Force, got a background with some remote sensing. From there, went to the National Geospatial Intelligence Agency, did some more, and really saw that there was a gap for Alaska in the Arctic, Greater Arctic, and being able to use kind of the new technologies with artificial intelligence and these different data sets to be able to adapt to climate change. And so that's when I called my co-founder. In 2018, we started Pole Arctic. We started with doing a sea ice forecast, from there, we really realized that we needed to understand like the nearshore bathymetry for the sea ice. And when we were doing the mapping for the nearshore is really when we saw that there was a lot of application for fisheries as well. And so we have kind of those three main areas in Polarctic that we've been working on.
Great, thank you so much. Richard, as the CEO of Vision Foresight Strategy, can you tell us a little bit more about yourself and your organization?
Yeah, I was born and raised in Hawaii, which was a tough gig, so you're all welcome. My degrees are in political science and future studies, and future studies is a relatively unknown academic field. It is centrally concerned with trying to understand and anticipate change in society, and then through that process, you're trying to develop foresight. You're trying to use that foresight to help folks reframe both what they expect to see happen as well as what they want to see happen. And so we work with organizations across all three sectors, helping them do a variety of projects that range from pure foresight projects, really where they're just trying to have a conversation about what's the future of X on one end, to strategic planning on the other. And most of the projects are somewhere in between. So it's a lot of what's the emerging landscape of the future? What are the different directions these things could go in? How do we think about that? How do we prepare for that? Where are the threats? Where are the opportunities? How does that impact strategy? So that's the kind of work that we do.
Great, thank you so much. Clay, going over to you, can you tell us a little bit more about yourself and Cordova Electric?
Sure. My family moved to Alaska when I was 5, so kind of a lifelong Alaskan, and graduated from University of Alaska Fairbanks with electrical engineering degree, was staff engineer at Kodiak Electric for a few years, and have been at Cordova Electric here for the last 26. And I've had the fortune to work with great teams, including ACEP and others, to work in pretty challenging environments to keep the lights on and do it affordably and make the energy accessible and locally sourced, so secure and sustainable for the communities. And in a small microgrid environment, you get to work on everything from a customer's toaster to the advanced controls and complex technologies we're folding in now. So that's it in a nutshell.
Great, thank you all. And so to the audience, this is going to be a facilitated conversation. What I'd really like to do is, as the questions come in, I'd like to ask them of our panelists. So please, as we have this conversation, please feel free to put your questions in the chat and we'll integrate them into the conversation. So Leslie, starting off with you, when we first connected, I was really intrigued with the role of AI in community determination through your work. Can you tell us more about how the use of AI and mapping can help communities make decisions, specifically regarding infrastructure development and the protection of subsistence areas?
Yeah, absolutely. So what we use artificial intelligence for a lot is our environmental forecasts and understanding kind of how the climate is changing, how the land is changing, things along those lines. So a great case study for this is we worked with a community who wanted to develop not only a commercial inshore fishery, but be able to understand where they could put some infrastructure, where they could adapt for different shipping channels for tourism, things along those lines. And we were able to take a bunch of different data sets. And one of those was actually traditional indigenous knowledge, because working in the Arctic, there's always a challenge trying to get enough data, especially environmental data. And this group happened to have a lot of the elders who were talked to, and they understood where different species were that they found, and were able to provide that information. Because we were doing it for the community, we were able to protect that information for the community as well. So we're not publishing on that information or sharing it outside. And so it's important to be respectful for that. But we're able to take that information, take that along with remote sensing for total suspended solids, sea surface temperature, currents, things along those lines, map the near shore of their islands, which hadn't been done. And when we did that part, we actually thought there was a big flaw in our model, because we ended up finding this uncharted subsurface seamount that wasn't on any nautical charts. And so we saw like this underwater mountain range. We're able to identify that went and talked to the community. The community actually knew it was there, but it wasn't in any of, again, those Western like sea charts. So we were able to take that updated all the current models that we had of like how the water flows. And we were able to take that, their traditional indigenous knowledge, train an AI model, extrapolate into new areas that they were able to identify for potentially subsistence activities, but then also commercial inshore fisheries. And to be able to identify, all right, what areas do we need to protect? Where could we look at building new infrastructure? Where would we want drainage pipes to go? Things along those lines. And that all of that information kind of came together to be able to help that community determine what it wanted to do and how it wanted to do it, and to grow and to help the community members as well.
That is so exciting to hear how this emerging technology can actually help protect some of the generations of knowledge and practices in these rural Alaska communities. And I'm seeing that we're getting applauses and hearts and thumbs up for everything you said there. So a lot of positive reaction there from the audience. And I think when we circle back, we'll go deeper into those points there. So Richard, in your work, you focus on understanding what's coming in the future and use that to help leaders be better prepared. I know AI in particular has been of interest to you, especially in how it may be shaping the future workforce. Can you tell us more about what you're learning and how leaders in various capacities should be thinking about AI as it relates to the workforce?
Sure. And first, let me thank you for putting me after Leslie after she does that amazing case study and that really cool work that she's doing. Now, let me follow up from that. Yes, I think across all of our clients, across sectors, and across all the various industries, AI, big AI is a central part of their strategic conversations for all of them. And I think, when you're looking at it from the point of view of sort of senior leaders and employers and stuff, you've got a number of different drivers going on, right? So coming out of the pandemic, we have the whole workforce shift, right? So the whole work from home, the whole hybrid thing, and this big difficulty that most of our clients talk about in terms of getting employees, finding and recruiting the right talent. Like it's just become a lot harder for them. And at the same time, you have this other driver around these very stark generational differences between how different generations from boomers to Gen X to millennials to Gen Z, how their attitudes towards work and work life. And some of those differences are pretty pronounced. And so a lot of the leaders that you're talking to have this very big and sort of growing interest in AI and machines and what they can do, right? They're having a hard time finding the employees they need. They're concerned about workforce over the near term and the long term. And frankly, a lot of them are really excited about how can I replace employees? How can I, not have to hire new employees? Frankly, that's part of their conversation. And a lot of them also are very intrigued with these things. They're trying to understand how can they use these things to augment their workforce. And, I think we all had talked about it previously, in talking with them and in sort of observing the space, one of the things I'd probably say, if I had my druthers, we would stop talking about AI as a big monolithic thing that came down onto the mount. They're tools, right? You can think of them as tools, right? We all had to learn computer programs. We call them apps now, and I don't quite understand why, but we had to all learn computer programs. There's Excel, there's Word, there were PageMaker, right? There's all these different programs that we had to learn. And these are very much the same thing, right? When you're looking at AI, and this is some of the conversations that we have with clients, these are tools and they are built off different approaches and different models. They're designed to do different things. And so having to understand kind of that ecosystem of what these tools are and what they're good for, how you trust them, where you don't trust them. And so, I think when we sort of come away from some of these conversations, the kinds of things that we're talking to leaders about and the kinds of things I would sort of recommend is in the same way. I'm Gen X, so I'll cut cop to my age, right? Like we had to learn the internet when it came out. We had to learn websites. We had to learn all those new programs. We had to learn email, all of those things. This is unfortunately for leaders, a new set of things to learn, right? So it's time to learn this ecosystem of tools. They don't have to become experts in it, but it's time to really get familiar with what they are conceptually, how they work, where they're good, where they're not good. And then I think, a lot of the conversations it's trying to help folks look at their organizations. And with these tools, you're asking, these basic questions. With the tool that we're debating right now, with the tool that we're thinking about investing in, with the tool that we're trying to learn more about, is it going to replace human labor or is it going to augment it, right? There's a huge politicized debate right now about, are these things going to take all of our jobs and yada, yada, yada. But when you go across the history of technological innovation and how it impacts economic life, you can break it down into these fundamental two different things. Will the new tool replace human labor, right? Thus radically changing sort of what we do and how we do it. Is it going to augment? Is it going to allow a person to do more than they could do before? Is it going to allow a person to do different than what they could do before, right? And I think with the variety of these tools, that's a better way to sort of, for leaders to think about these things and talk about them. And then I think the final thing, and I think we talked about this previously, is just kind of that idea, right, that you're looking at this stuff and AI's gotten interwoven into so many aspects of life that most of us don't even see or understand. It's already sort of woven in there, but it's trying to understand like kind of that idea that AI becomes the UI, right? AI becomes the user interface, that mediating layer between all these tools, and thinking about it as it potentially gives users access to skills and information that would have been really hard for them to get access to and to use before. But that's the kind of conversations that we're having with various leaders. And they're all interested in it. They're all trying to understand it. And they're all worried about keeping pace with the developments and keeping pace with their industry and where their industry is adopting these things and how they're adopting them. I'll stop.
Great, thank you so much. And we've got more threads to pull on that one as well. And please, again, as a reminder, please put any questions you may have in the chat. So Clay, moving on to you, Cordova Electric Association has been taking a leading role in understanding opportunities for AI within an electric cooperative. Can you tell us more about what you're hoping to achieve?
Absolutely. And yeah, it's fun to be on the tail end of both panelists here and talk about the application side. And that's where a lot of the conversations around AI are revolving right now, and innovation is application, the tools, as Richard said. But there's underlying infrastructure that has to support that. Data processing is very energy intensive. It puts demands even on our national grid as we look at the hyperscale data processing centers in a way that can degrade those grids. And in that ecosystem, of course, AI is putting tremendous pressure on compute capacity, and supply chain issues and other bottlenecks are going to make it difficult for our compute infrastructure to keep up with all the applications that are just exploding. So that's a real challenge. And of course, in a supply and demand environment, as the demand outstrips the supply, access to data, the cost of data are going to be going up. So these are some of the things that really concern, me as a utility manager in a remote environment where we're using more and more of these cloud-based technology tools to manage our grid and make this energy transition. And so we start worrying about access. We worry about the viability of the communications links that connect to those processing centers. So we find ourselves in a place where we're collecting real high resolution data in our electric utility, in our ocean science research, work that Leslie does. That data all has to be hosted somewhere. So we ship all that data down to a server, who knows where a lot of that data gets analyzed, processed, and then we have to ship it back for the useful information. So when we saw an opportunity through GreenSpark, a small edge server startup with roots in Alaska, actually providing an opportunity for us to host a local area cloud on a very environmentally responsible platform in a way that supports our local businesses and our social equation, and whether it's education and so forth, we kind of jumped on it. And so didn't fully appreciate all the opportunities when we made that decision a few months ago, but it's really coming home now as we start to map out some of the use cases and so forth. So at a high level, we GreenSpark installed about 150 kilowatts of compute in one of our hydroelectric plants, where we're using the cold water in the pipeline to cool the server. Because it's already in an enclosed cabinet, they can put 10 times the compute density in a small cabinet. And then we even take the warm waters that comes off the server and exchange that heat into our power plant. So for, the immediate benefit stream for the utility, of course, is power sales, energy efficiency, some lease space for a customer. But then having that local area cloud available in an open architecture that can host Amazon AWS, Google Cloud, Microsoft Azure, or individual applications, including our own cybersecurity software, which is monitoring and listening to our highly automated grid and telling us if there's bad things happening in there. Those applications can all be hosted right in our own backyard now. But then you think a little broader, like our local tribe, the Eyak tribe, their language is extinct, unfortunately. But fortunately, they were able to capture that language from the last of the language speakers through a long-term project. So their entire language is hosted on the internet somewhere. Wouldn't it be nice if you could bring that home and host it, on a server that's located right on their own traditional lands for data sovereignty, processing? So application, but getting back up to the higher view, this really stands at a new and unique intersection of data, telecommunications, and energy. Because now these servers, you can flex the amount of data load you have on them. And we have excess renewables at time with our hydroelectric plant. So now we have a great handshaking on the energy side between these servers, where instead of spilling excess hydropower, we can now sell it to a customer who can get a better price for that, offer a green platform for their services, and not only locally in Cordova, but regionally, as Cordova Telephone Co-op has built out one fiber connection now, but two others in the pipeline. So have triple fiber connectivity in and out of the community. So we have the ability to host not only local cloud applications, but host those regionally. And we don't have the latency, the time involved with the round trip. We're taking all that data bandwidth off of the communications networks. So there's an opportunity that we're pursuing to kind of co-optimize, again, that intersection of energy, data, and telecommunications in a way that's beneficial, and instead of degrading to the grid. So that's a lot to get my head around, and maybe we'll just let that sink in a little bit and stop there.
That is fantastic. I had no idea that they were preserving an extinct language on the lands of the people. That is a phenomenal story to tell.
Well, it hasn't happened yet.
Oh, okay.
It's an opportunity.
That sounds like a fantastic opportunity. And as we look at opportunities for Alaska, data centers have been a part of the conversation for a little while now. And two of the challenges are really the cost of energy and connectivity and speeds. So the fact that we're finding ways to put these in communities for mutual benefit, it is a great story, especially since, as you were talking about excess renewable power being able to lower costs of energy. That's a fantastic thing for us to take into consideration for communities across the state. Looks like you were about to say something onto that. Otherwise, I can move on to the next question.
Well, yeah, I would just add that, data now offers an opportunity to become an anchor tenant. So say you have a coastal village that is trying to develop wind or solar or tidal or intermittent renewable, and they really don't have the economy of scale or the capacity. And so now you can solve two or three problems at once, right? With data hosting in their environment, that becomes an anchor tenant for their energy in a way that, again, helps their energy rates and helps their energy sales, but also brings that data hosting home for them. So literally, it's a digital divide between, kind of the NFL hyperscale cities that all have, access to data and so forth to kind of these remote and underserved environments where I feel like we're just kind of holding on by a long thread. This almost moves you to the other side of the digital divide to where we have the energy resources, we have local energy resources, we have a lot of resources we can bring to bear to really kind of jump from being left behind to kind of being out front.
Absolutely. We just had a comment here talking about Richard's note as AI as a tool, and that kind of leads us to the next question, the broad one for the group. Richard, you started us off with what is AI and what does that mean? Is that even the correct term? Is artificial intelligence the correct term, or are there better ways to explain the nuances? So far, we've already heard apps and LLMs and MLs and chatbots. So when we say AI, what do we mean, and what are some better ways to maybe address those tools?
I'm sure we could organize a day-long argument over how to define AI. I and Leslie actually builds them and stuff, so she's gonna have a very informed opinion on this. Um, I've always preferred thinking about them as machines, as tools, like because when we just again that monolithic AI, it conjures up for Americans, it conjures up Skynet or Jarvis or or a really really smart R2D2 kind of thing, like can do anything. And you can get into debates around intelligence, whether it's really intelligence and whether it can do deductive, inductive, or abductive reasoning, yada yada. You can get into all of that stuff, but I have preferred thinking about them as machines, and I prefer talking about them as machines. And they are tools, right? And when you start to play with them, you do start to learn, like, oh, it can't quite do what I imagined it could do, and I can't just tell it like, yeah, put together that report for me, and it understands what I'm saying just based on all of this stuff. Not yet. And so I preferred thinking about as tools or machines, and then when I do that, for me, it reframes. There's this growing ecosystem of machines, right? There's this digital landscape of stuff. So, when we talk about AI as the UI, we're talking very much about this generative AI and this layer, this interface between a lot of these other tools. But more expansively, I think if you want to understand and anticipate how these things could develop and where the opportunities are, all of these machines, because they're digital, they're part of this landscape and they can be connected to each other. And so, when you have an organization, they're trying to understand what can they do with these things, you're trying to expand their viewpoint so that they're not just going, what can I do with ChatGPT? It's like, how do I see this landscape and all of these digital tools and all of these machines, and what are the different ways that they're potentially going to evolve? What are the different directions different developers are pushing these different tools in? How can I connect these in ways to create systems that are really, really useful and beneficial to me? And there, in that chat comment, there's a related issue. Over the years, we've often tried to encourage folks, especially communities that typically have not been pushing a lot of these big technological changes. There's an often mistaken idea in the history of technology, particularly coming through the 20th century, that you'd have a technology, somebody developed something, and people would look at it, for example, waves of these things, and they would look at it and go, oh, this is great. This is going to be great for democratization, this tool. But the tool wasn't designed for democratization, but people tried to apply it for that. And often they don't quite work the way people want them to. They don't quite do those things when they're trying to adapt the tools. And it drives this notion of, if you want a technology or a system to create certain outcomes or to reinforce certain values, you have to design it with that in mind. Otherwise, if it's able to do that, it's an accident that it's able to do that. And so, we talk about social media. Social media wasn't designed to create a cohesive society with great outcomes. That's not what it was designed to do. That's not what it was evolved to do. So if you want a technology to increase democratization, you've got to be part of designing it so that that's what it's about, so that's what it's architected to do. And as you're building systems of systems, I think so. communities, regions, organizations, groups. I know it's not easy, but if you want the technology to help reinforce certain things, you have to get in and build it. And one of the cool things, and again, Leslie's a much better position to talk to this than I am, but because they're digital tools, and just like the last panel, speaking to, it's a lot easier for way more people to become users and developers of these things than, say, in an age past when you had to build a factory to be a player. So it's just a different environment. I'll stop.
You mind if I
Leslie,
jump
sounds
in?
like yeah, absolutely.
All right.
Please do.
Yeah, thank you. I have so many thoughts as Richard was talking. And so I think part of it is, so when we talk about AI, we have absolutely had that same effect on people. And they are like, Skynet, transformers, all these kind of things. And really what they're thinking of is artificial general intelligence, or AGI. And that is a whole nother ball game. And that's like, when artificial intelligence can do all of these other things that we attribute to humans. That we are not there. And there's some interesting discussions and some arguments on how AI is able to do so, especially from some of the generative AI and how it is able to do what it does. But right now, what Richard said is absolutely true. It is a machine. You can think of it as really fancy math, is another way to be able to think about it. And I think it was great because you had the panel before us was talking about large language models. And what's really important too is to recognize in AI is there's lots of different architectures and how these architectures applied to different sets. So large language models are a transformer architecture, and that gives them the ability to be able to identify these different next token and what statistically comes next after a word, and it's able to put all of this together. And we use in our environmental forecasting lots and lots of different types of architectures. We use like UNet architectures, convolutional neural networks, generative adversarial networks, GANs. There's so many different types of architectures that like you just gloss over when you say AI. And one of the things that we're able to do as kind of a consultant is bring that kind of expertise to the communities and the groups that we work with. And I think that's really important because we're choosing the best architecture to use based on science. So my co-founder is a physical oceanographer. She knows the science of the ocean. And when we're doing a lot of our environmental forecasts, that is really important when you're looking at the architecture that you're using to be able to design it in a way that gives you actually great results. Otherwise, you're throwing data into a blender and you're, getting something out, and you're not understanding what your architecture is training on. And there are some huge pitfalls for that. And it can really hurt people and it could become a big problem. And I think that also really plays to Richard's point of saying that like more people can understand these, and they should, especially for communities, because as more of these AI algorithms are starting to decide and dictate into society of where things get built or who gets what and all of these different things, you need to understand how the algorithm, what the data was used, the architecture, all of that. Because if you need to understand why it's making that decision, like there's a great example of AI that was trained to identify boats. And they were able to take the AI and was able to identify the boats. It did really, really good. And then it found out that it wasn't actually trained on identifying the boats, but the water. And if your AI is trained on the wrong thing because you just threw data into a blender and you didn't understand it, then there can be huge implications down the line as it's making decisions. So again, really important to have that technical expertise and knowledge to be able to make those in the right way, to make sure that those second and third order effects are where you want them to be, and you're not including weird biases in your data and your algorithms as well.
that brings up such a great point. I was at a conference a couple weeks ago, and they did a similar story where there was an effort to train an AI to recognize fox. And when they ran it, they found that it was really good at identifying squirrels. And what they learned is that they taught it how to identify snow. And so, like, that really brings me to a next question. Can you tell us a little bit more about how you trained the AI model you developed? Specifically in terms of subsistence areas. And then we had a question earlier, and I think this dives right into it, hallucinations versus reality. So where are our limitations? How do we train our models? Where do we understand where those boundaries of accuracy are? And how do we know what data sets to put in to make sure that the results we're getting are realistic? Leslie, I'm looking straight at you, sorry.
Okay. All right. I just got off on my soapbox, so I was worried about getting back on, but I'm going to. So I think it's so important, again, to have the groups and the people to understand the types of algorithms and the data and the science behind it. And to be able to do the quality control and the testing to understand that as well. There's a big trend in artificial intelligence now called XAI, or explainable artificial intelligence. And instead of just doing throwing data into a neural network and then being like, it's trained, it's to be able to identify what it's trained on and all of those different parts. That's where I think it's really important, especially as people are contracting out with different groups and things, to be able to know that who you're working with has the ability, the knowledge, the data, just the know to be able to create those. So for us, for what we did for the subsistence activity, we're an Alaska Native group. Like me and my co-founder are both Yupik Alaska Native. And so that was one of the real strong points that we had going into this, because we actually value the traditional indigenous knowledge. And I know there's a lot of challenges to that, because a lot of different groups believe that it's not scientific data, it's not Western science data. And but there's a lot of real great value with it that is different from Western science, from an observational perspective, from its historical value and created over time. Like the fact that the community knew about the subsurface seamount, had a name for it, but wasn't on any nautical charts. Like there's a lot of value in that traditional indigenous knowledge, which is also why I made the point that it's really important that we protect and respect it as well, and that it's not used for exploitative reasons, and it's for the community, and they should be deriving some sort of benefit for it. So what we did for that one, we had to map their nearshore, because again, it hadn't been done. Very similar to a lot of places in Alaska where the nearshore hasn't been mapped for over 100 years. And last time it was by like lead line. And this is a big challenge because you have a lot of erosion, a lot of things are changing for the mudflats area, and it becomes really dynamic in that nearshore, shallow nearshore area. So we were able to map the nearshore area and take that information along with, like I said, the total suspended solid, sea surface temperature. We remapped currents and how the water flows because it was wrong. And and that was really relying on that science of oceanography. And then the traditional indigenous knowledge, I like to say it was geospatially referenced, because what happened was they went to the community and talked to everyone in the community, and they showed them a map and they said, where do you catch different species? And they were able to draw on the map and say, here's where we catch scallops, and this is where we find polar bears, and this is where we find eider ducks. And they were able to go through all of this kind of information, and we had thousands and thousands of information. We were able to take that information then and rasterize it. And rasterizing is when you have like each pixel has a value. And so based on where they said they found that information, we were able to then give those different values to then take that and to train AI with that and the different remote sensing information that we had. And so all of that together, then we were able to train and identify the locations where they did, the different things that happened in those areas, and then extrapolate to new areas as well. I don't know if that answered the question or answered it too much.
That is incredible. No, the fact that we're able to use tools to do that is really interesting. So, and again, we saw some reactions there from the audience on those comments. So thank you so much. And we did talk a bit. In fact, you noted it a couple times, the importance of protecting the data and the information. And so something that ACEP in particular is working on with in partnership with our communities is that data sovereignty aspect, making sure that that information is protected and used in a way that is at the benefit of the community, and it's their determination to say how that information is used. So the fact that that is a priority for you and the work you're doing is really awesome to hear. So on to that, we do have a question for you, Clay. You may have had a chance to read it here in the chat, but since we're recording, I'll read it for the group as well. This is relating to the data center that you were talking about and the heated water going back into the power generation system. Could you talk more about that, including what's being done and opportunities for the future, focusing on what we need to do to make that the norm or mandate for data center heat? And how would it be responsibly used in an environment with threatened permafrost? Heat, just like carbon capture, seems to be a no-brainer here too. You have any thoughts on that question there and a response?
Always have thoughts and opinions. Yeah, so specifically what we're doing is just as the cold water goes into to cool the data server, it's warmed up. So we're just running it through a very simple heat exchanger that takes the heat back out of that water and blows it into the power plant. So in winter, we have electric heaters that are heating that plant. Typically, very often we're generating with diesel fuel. So those electric heaters are actually a big electrical load that are causing us to burn more diesel fuel on our grid. Now, the data center, there is a host. Yes, it's an electrical demand on our grid that's causing some diesel use, but we're making it as efficient as we can by making sure none of that heat goes to waste. That's a huge opportunity for Alaska, where heat is very often a multiple of the cost of electricity and much more valuable. That's why some of these technologies, nuclear, for example, we think of it as an electrical plant with waste heat, but is it really? I mean, if we thought of it as a heating plant that produces electricity, it kind of changes the thought process and really values that heat appropriately. So it's a great question. And in the context of permafrost, we have Alaskan developed technologies, thermal siphons and so forth, where you can passively pull that heat out of the permafrost. So why not put that into a building or into beneficial use rather than just releasing it back into the environment? I think there are a lot of opportunities. And again, this is thinking holistically about energy, just not heat over here, electricity over here, transportation over there. Think holistically about how can we look at the whole energy picture and get the highest and best use in the most responsible way. So good question. But if I could just talk a little bit to the former discussion of the panelists. The great thing about being in this career for a long time and in one place is I've seen Cordova Electric transition from 100% manually operated power plants where push buttons and pull levers and walk around with clipboards to 100% automated. So we've had to spend years thinking through what do you want to automate and what don't you? Where do you want a human operator in control and when? And when do you want machine learning tools and all these fantastic artificial intelligence? To Richard's point, really it's just collecting data and analyzing, processing it, making it more accessible to humans so that they can make better decisions. So we had an event where we had a lot of snow on the ground, a lot of heavy rain. One of our small hydro projects, I'd said for years, there's no danger of ever having an avalanche there. Well, by gosh, an entire mountainside liquefied and flowed down through the valley, all the way through the power plant, all the way down to the ocean. And it pushed a big wall of water in front of it and then a big wall of slush. Thank goodness it's a remote site. Nobody was in that canyon or on the project works, or it could have been disastrous. But we had all the data to look back through our trends and everything and say, oh, look, here's where the water was rising. We know the background conditions with wet snow and heavy rain, warm rains in the middle of winter. So we could very easily program an algorithm and embed it in our automation system that if these circumstances are happening, and we see the water suddenly start rising in this project, issue alerts and klaxon horns and stuff, but then start shutting that plant down. That plant said, oh, more water, and started opening up valves and trying to produce more energy. And then the slush hit and shut it down, and we almost had an outage. Fortunately, we carried through. But anyway, so kind of defining that man-machine interface and what you want machines doing and machine learning and tools and what you want humans doing. And in general, we've kind of rationalized around if it's very normal, stable, repeatable conditions, that's where compute shines. You've got steady inputs, you can make decisions in a normal environment. But when you start having degraded situation where you're having fierce storms, unusual environmental considerations, broken equipment or degraded equipment, that's when I want one of our operators at the controls. And great thing. The beautiful thing about AI now and having all this data and having an automated system and having a digital twin that's been built for our grid, we can set that aside and do all kinds of scenarios, even train operators on a digital platform instead of having to do it live on our grid. So lots of fun stuff.
Great. Thank you, Clay. And we're actually going to be learning more about that digital twin after this panel. So looking forward to hearing that presentation. So we're talking a lot about data sovereignty, how you do AI. Questions that came up in the last panel related to data privacy, access, cybersecurity. What are some key considerations that leaders in communities or even developers should take into consideration to make sure that what is being built is being used appropriately? So if you had some lessons learned or some key takeaways that you think that as businesses and industries go into this vein, what are things that they need to think about ahead of time? So Richard, I would love to kick this off to you first.
I'd say, in hanging out with various leaders, some of the top concerns have to do with they have different terms for it, but when they're deploying these systems in-house, accidental discovery, inappropriate discovery, the release of that information because they're in-house, they're deploying some of these tools, right? These particularly the generative tools. And to go back to one of Clay's point, right, this is all built on an infrastructure, and information infrastructure still matters. And so if the information administration and the policies and the data management and all those things have not been maintained or structured in the right way, you start deploying these systems and people are without meaning to, they are accessing, sharing, disclosing information, data that they're not supposed to have access to, or the systems are drawing on data that's outdated, that shouldn't be there, right? So there's all these little, and that's just small operational type stuff. But a lot of the leaders are very much worried about like confidential information, because the systems, again, if you don't build that information architecture underneath in the right way, these tools don't know they don't know, oh, heck, we're not supposed to share that piece of information. They're just like, ingest, let's do this. And so those are some of the more operational things that leaders, at least we hear them stressing about and talking about and whatnot.
Great, thank you. Leslie, in your experience, especially with protecting the data sovereignty of the groups that you work with, what are some key considerations that either you or those communities need to consider for access and privacy?
I would love to see more Alaska companies have like a data and an AI strategy. I think that's going to be really important coming up. And I think that a lot of people are like, oh yeah, we have to have an AI strategy. How do we use ChatGPT? And you're like, oh, no. There's so much more than that. And I think there's a lot of groups and companies that have, just like Cordova, amazing data and potential to be able to harness that and to be able to have a strategy going forward and looking for different ways to be able to optimize or use that in ways that are unique for Alaska would be fantastic. So I'm hoping to see more of those coming out and less just about maybe the large language models and more about for communities and different engagement.
So pulling on that thread a little bit more, are there any good strategies that you found, or what are some good resources that leaders could look to have kind of an informed development of such a strategy?
Gosh, so it really depends on what each group or organization is really hoping to do. I would say there is not a blanket, and I probably would look at Richard more for more guidance for just strategy wise. But I would not say that there is one strategy in general that would be one size fits all. And I think it really needs to come down to the values and the goals and what the each organization would want to do. So Alaska Native organizations might have different goals than ConocoPhillips kind of thing. So, but each one of them should all have, like going forward, what are we looking for? Are we trying to use the data that we have? Are we trying to go into new markets or things along those lines? They could look at it from lots of different angles.
Great. Thank you, Leslie. Clay, you've already got some experience having to work with data access, cybersecurity, data privacy. Can you tell us a little bit more on your thoughts on some best practices or lessons learned, or maybe some, just your thoughts on your approach there?
Yeah, it's what keeps you up at night. I mean, the challenge with technology in a highly automated grid is that if somebody can inject false data into a system or access your system and take control of it or parts of it, then that's a pretty concerning vulnerability. So we worked with the national labs and did deploy some next generation infrastructure architecture so that, like between our power plants, they're segmented, they're firewalled from each other. So maybe you lose part of your system, you don't lose the whole thing. And then you want to protect your physical data and so forth. But in the context of AI and access, one of the things I like about the conceptually about a local area cloud is that it's physically located in your environment, and you kind of know physically what's hosted there. Maybe a little bit less of an attack surface or global access than a hyperscale server, for example. So just a smaller footprint, maybe a smaller target, and we do go through those thought processes. And I guess I'd just say that.
Thank you so much. We got about 2 minutes left here. So going around the room, is there any final thoughts regarding the role of AI, opportunities and challenges that Alaskans and others should be considering? I'll start at the top of my screen. Leslie, any final thoughts?
Yeah, again, so the big thing that we're working on now is fisheries and being able to understand that. And if you could just tie it to the power side, then if you're looking at offshore wind or if you're looking at different things, I think being able to use artificial intelligence for the different fisheries would be a really neat way to be able to understand and capitalize on that. So I'm obviously very optimistic about the different ways that we can use AI because I think we've done some really cool stuff, and I'm hoping that we get to do more in Alaska coming forward.
Great. Thank you so much. Richard, any final thoughts?
Yeah, I think there was for the longest time, right? We had computer literacy and we were trying to get everybody trained to understand computers. And more recently, there were all these debates about should every kid learn to code and all that kind of stuff. And of course, now ChatGPT makes it so I don't have to code. But I think sort of in the broad space, right, there seems to be genuinely an opportunity if these are tools and if we can broadly disseminate sort of access and sort of basic familiarity and understanding with these tools, you want to get these tools into the hands of as many people as possible so that they can experiment and build solutions to local things, right? Like you want to get that out there, you want to diffuse that, you want to let lots of experiments happen because these tools can be put together in so many different ways. Look at what Leslie guys did, just with a unique combination of things, right? So to me, the broader sort of opportunity is just to use these tools and to as potential solution builders, and we just have to get them out there to people.
Great, thank you, Richard. Clay, you want to close us out here?
Yeah, my first takeaway is it's fun chatting with Leslie again and Richard, and I hope I can bump into him at the Sustainable Energy Conference. But just to build on some of their comments, fisheries is 90+% of our total economy here. So the opportunity to use drones, new visual imaging to actually identify which species of salmon. We can do stream surveys. If we're experiencing some of these dynamic climate of droughts and floods that some are unprecedented, that pose threats to the resources, using these tools to have more not even real season in season fisheries management, but even moving towards real time management helps us better protect the resources when they need it, harvest the abundance when it's available, and just be a little more deliberate in what we do there. And then to Richard's point, again, technology is a tool. So as an organization, what's most important to you? There's a lot of exciting things about energy data infrastructure, and I think we really need to be looking at that in our Alaskan communities. But first and foremost, as Cordova Electric, we want to, again, keep the cost of energy affordable, reliable. Think holistically, what are other ways that this can benefit the community by hosting an AI lab for our school and so forth. So really remember that technology is a tool, and it's important to be very thoughtful about, as both Richard and Leslie have said, how do you use these tools and do it deliberately, think about it holistically, and talk to experts like them to help you map it out.
Great, thank you so much. And we should note, since you brought up the conference, you are actually going to be coordinating or at least participating in an AI panel there. So we hope to see all of you at the Alaska Sustainable Energy Conference and hearing more about AI and the opportunities. Welcome back. Thanks again for joining us today. Next up, we're going to be hearing from Jay Byam, the Chief Executive Officer of Cartorium, to learn more about digital twins, where to start. Jay, thank you so much for joining us this morning. Do you mind starting us off with a quick introduction of yourself and Cartorium, and then take it off from there with your presentation? For the audience, please continue to put questions in the chat, and I'll be back when Jay is done with his presentation. Jay, the floor is yours. Thank you so much.
Hey, everybody. My name is Jay Byam. I'm presenting today on digital twins, and really want to harp on some things that I harp on pretty often. So if you've heard me speak before, sorry, not sorry. A lot of the same stuff you're going to hear, but I think it's an important conversation to be had. So essentially, what I want to talk about today is give you an overview of who I am, who you're hearing from, I suppose, really just give you some context on where all these opinions are coming from. At least so you'll understand, where I'm coming from. If you want to agree with me, obviously that's fine. And a brief overview on the company that I run. We are a digital twin software company is what we call ourselves. So I want to explain what we're up to real briefly, again, just as more context to the discussion that I want to have today. And then the real sort of point of the talk today is to talk through what is a digital twin, what is digital twin as a concept, what are different things that different people say it is, and what is it actually, et cetera, et cetera. And what I really want to do is break it down as rather than arguing about a very specific definition of digital twin, I like to think of it really as levels of digital twin. I think it's a more useful, more inclusive, more usage-based, I suppose, definition or way of thinking through the concept. So I want to present that today. And then I want to sort of end with an actual example of some work we've done here in the state that I think exemplifies how to go from nothing in terms of Industry 4.0, digital twin, AI, really nothing in terms of those things, and what it looks like to start to get those returns on investment from this kind of technology, and hopefully use that as an example of how to demystify these things, and then walk through briefly at the end how that sets you up to then move further up those levels of digital twin once you have certain ducks in a row. how does that lead you into the next things, and how can you begin to take those steps? And we will certainly have time for discussion at the end. I'm not taking up the whole time with this presentation. So that's what that looks like. So brief history of me. I grew up in Delta Junction, Alaska. If anybody's ever been up that way, I went through the University of Alaska Fairbanks, master's degree up there in computer science. So my background is in software development, and then moved into software consulting throughout my career, working across a few different sectors, but really broadly, mostly with what I would call asset-heavy industries, are the kinds of companies I've worked with throughout my entire career. And I like to say it's companies that manage big, expensive stuff. That's what I like to say. But really, it's organizations that are characterized by their reliance on physical assets. And I like this slide because obviously, if you're familiar with Alaska at all, or if you grew up here, if you work up here, there's so many examples of these kinds of organizations. But really, it's a global phenomenon, right? Physical assets that make up sort of the bulk of what a particular organization is managing. And so, having worked with these kinds of organizations throughout my entire career, and with Cartorium as well, we start to see these patterns that really, in order to make the day-to-day decisions that need to be made for work planning, for troubleshooting, for operations and maintenance, there are many different streams of information that go along with this. And so you've got things like your asset management, workflows, operations and maintenance, work order service histories, that kind of bucket of things for managing, actually a human doing something to the physical asset to keep it working. But you've also got your building automation, your SCADA. This is, metering, sensors, building trends off of those things in the best cases. But also the more static stuff, process documentation, desktop procedures, maybe training manuals, things like that, that I think are kind of the unsung hero of a lot of these kinds of organizations. These bottom two on the left, more and more being utilized. CAD models, 3D as-builts, things like that. Again, if you have a physical thing, whether it's a facility or infrastructure or whatever, it's really helpful to have a visual representation of that thing for work planning, for design, et cetera. And then on the more broadly spread out type infrastructure use cases, GIS is very heavily used as well. Maybe not as heavily as you'd expect by certain organizations, but GIS being those mapping tools, geospatial information systems, GIS. And then the last bucket of information, again, that I like to point to when we're talking about what goes into the day-to-day with these organizations, I find that honestly 80 to 90% of decisions made come from someone's brain, right? I mean, just off the top of their head, they've been with the organization for so long that they just know what needs to be done. And so I think it's really important to also capture that there's a human expertise element to everything that goes into these kinds of organizations. What we start to notice then, I guess, from a data standpoint, is that because there are so many different layers of information, go with me on this, there's so many different layers of information. Many of them, there's too much friction between these different data silos, to use a super overused term. But I really do see it happening where, because it's too difficult to get to that information, I'm just not going to use it. I'm going to just move forward, maybe with a guess, maybe with a less efficient way of going and getting that information myself. Things like that. A really common example I like is, maybe an operations team needs to know how much space is there between these two things out on the plant floor. We could just, reach out to the engineering team for them to bring out their as-built and give us a measurement. But we don't like those guys maybe, and it's too difficult to work with them. So I'm just going to drive 50 miles out to the plant site and get the measurement myself, right? We see a lot of these kinds of decisions being made that end up being ineffective, lack of collaboration type operational environments. And there are things that make this even worse, this data availability problem, because of the high majority of these decisions that are being made based on human expertise. When that human leaves, you have this workforce turnover issue where they built up all that information and then they take it all with them. And maybe you end up with a situation where you contract that person after they've retired and things like that. Very, very common setup because of the amount of information that's stuck in a person's head and hasn't been institutionalized. And then, especially in Alaska, but also in other operating environments, you end up with very remote, harsh conditions is where these big, expensive things need to continue to operate. And that just adds logistical issues. One wasted trip because of rework, because you didn't bring the right equipment, whatever it be, that really adds to the logistical sort of significance of the different operations that are being done. Anyways, so from the Cartorium standpoint, we said, man, wouldn't it be cool if we could solve this data availability issue by bringing together all the visuals that are being used, drone flyovers, CAD models, GIS information, whatever, bring that into an accessible environment, and also all the data that people care about, from asset management to the automation to the sensing, and even have a place where you could institutionalize, where you could put all the information from your human experts and have that be an environment that can be collaborated in. And honestly, we came to this solution sort of backwards. We said, wouldn't that be cool? And we thought of it, and we'll call this, digital twin, I guess, and honestly, though, there's this way broader conversation that's going on around these things, where you're essentially combining visuals with data, and that is my pitch for the definition of this thing. And I actually really like this slide because I just got it from Shutterstock, and I think it's a really good example of something you might just see on LinkedIn, where it's you got all these dots and all the dots are connected, and that's digital twin. It doesn't really mean anything, and so what I want to argue is for maybe a broader, more useful definition of digital twin. And here it is. I mean, a virtual model of a physical asset or system or process, which is designed to accurately reflect its real world counterpart. I think the reason there's any argument at all about what is digital twin and what is not is because it's being approached from two different angles very, very often. The term came out of sort of the research community, where they're mathematically modeling and simulating real world processes, physics-based simulations, where they can run through things and then say, we should make these decisions based on these simulations. And later, as far as I can tell, the visual sort of revolution came around and said, well, it's also super useful for us to have a dimensionally accurate, maybe even photorealistic representation of this real world thing as well. And so you're coming at it from these two different angles, one being visual, one being more the simulation, mathematical modeling angle. And so if you hear someone say, what's a good example? You hear someone say, we built a digital twin to manage the operations of our micronuclear plant, and then what they show you is looks like a flow diagram, maybe some graphs, and you got some maybe red blinking lights. You might think to yourself that doesn't look like a micronuclear plant. I don't want to say anything stupid, so I won't bring that up, but that's the disparity. If you've ever experienced anything like this and you said, that doesn't sound like digital twin, you have these two different sides. Mathematical modeling and sort of what maybe some people would really harp on and say is the visual twin. We should call the visual stuff visual twins and not digital twins. Maybe that's true, but I guess I'm going to say it's too late. I think it's too late. Everybody is calling both things digital twin now, so it's just what it is. So what I want to present is a new way of thinking of this, that rather than sort of arguing over finer definition points, is an easier way of thinking through this, I think, that encompasses all the various definitions of digital twin in a way that, if you step through them level 1 to level 2 to level 3, actually allows you to gain returns on investment at each step, but also to move through the steps in a logical way that can bring you toward that level 3 sort of full paradigm shift of what digital twin can bring to you. And so what are these levels? What am I talking about? Level 1, I would say, is to start out with your visual twin, to use that term that maybe most people don't care about. What I mean by this is map out your system, have a reliable understanding, have that documented, have a comprehensive asset inventory, essentially. And when you're mapping it out, whether in 2D or 3D, have it spatially accurate. I think it's super useful to also make it photorealistic, and there are some great, reality capture technologies that can be leveraged for this, because then you also get that assessment piece. But I'll just leave that aside. And annotating that, then again, if you harken back to that previous slide where you saw those different layers, those different buckets of data that go into that day to day. If you can bring those buckets of data, whether static or live feeds, and associate them with their physical counterpart, organizing things in 3D in that way, super useful, quick way of finding what you need, of collaborating in a 3D space. Super usable in that way. Level 2, I would argue, is when you start to get into more of the IoT realm. You start to really talk about what is it that I could track data-wise. Once I've solved those sort of quick wins of, well, I know what we have, I know how to collaborate about it, I know how to do that work planning, but we need more information. And so I would argue you're moving into level 2 when you start to say, what sensors could we add? What could we track? What data feeds could we pull in to better inform our decisions, to have better transparency than just a static sort of drone capture in time, to understand really what's going on over time, but also in the immediate. And then level 3 is really what I would say is when you see a super flashy post on LinkedIn or something, I would say most of the time people are talking about the excitement of a level 3 digital twin, where you're really bringing in those AI and machine learning workflows, where you start to use words like predictive, proactive, and preventative maintenance for your asset heavy industries, condition-based maintenance, reliability-centered maintenance. All these buzz terms really, I think, are only made possible when you can get to the point of a level 3 digital twin, where you understand the spatial accuracy, the visual twin aspect. You've incorporated all of that data so that at this point you can actually build reliable models on top of that trending, on top of that data. Understanding your system as a whole is really what can be brought about when you have these other sort of ducks in a row, I suppose. And so if you like catchy phrases, which I really do, it helps me to remember things. For that level 1 digital twin, I would say really the purpose of it is that you can't manage what you can't see. If you don't understand your system, if you don't know what you have out there, if you don't have an accurate understanding all the way down to the component level, you can't really manage it in a holistic way. You can't really make proper decisions with all the information available to you if you don't have that information available to you, accessible to you, without digging through maybe some filing cabinets. And so level 2, then I would say you can't improve what you don't track. I would say the reason to move forward is we need more information. We've solved those quick and easy, collaboration type issues. But now we still don't know why such and such motor is failing, right? Let's get more information. Let's attach sensors. Let's track that information over time. Let's dig deeper with the data now that we understand where that data is coming from. And then level 3, I used to just have on here, release the Kraken, because I couldn't think of a good level 3. But I think what I really want to say about level 3 is that when you get to this point, you realize that some things can't be solved with humans, or some things can't be solved efficiently at scale with humans. And so let's go further. Let's leverage these technologies, these new exciting technologies that everybody's talking about. Let's pinpoint use cases for these. Now that we understand our system and we understand what we're tracking, we understand our problems, we know how to apply these exciting new technologies to specific use cases. That's what I would say is the point of going all the way, going to level 3 digital twin. And level 3, if I'll stop and mention this point, I would say Clay and Cordova Electric, they've got that level 3 going on. They're really going for it. And the reason you can tell is that they have built up sensors where they're pulling in real-time data and they have lots of historical data, what's the right word for this? Small time increments, essentially, so that they can have a really accurate mathematical model of what's going on. And based on that data, then build machine learning algorithms on top of it to be able to automate decisions within their grid. Again, a human can't react to this, situation that the meters are bringing in and telling us about our grid right now. A human can't react as quickly as this machine learning model or as accurately. So let's move that decision over to the machine learning model, solve that problem more efficiently for our grid. What I want to do now that I've sort of indoctrinated you, I suppose, on my levels of digital twin, is give you an example of how to go from level 0, which I kind of left off the slide, to level 1. And I want to explain what that does for an organization and the returns on investment that you can get just from going to level 1. Excuse me, because I think it's really important. This is, okay, hot take real quick. I actually don't like the betting big title of this workshop, because I don't actually think you should bet on anything. I don't think it needs to be a gamble. I think that you could make informed, data-driven decisions on what technologies to choose, and that at every step, you should be able to see a return on investment. If you have a vendor talking to you and they say, that first 10 million you spend, you're not really going to see the effects yet. You really got to get up to that 50 million, and then it'll be really cool then. I really disagree with that approach. I think you should really fine tune and understand what it is you're trying to solve at each level. And then hopefully, if your strategy is outlined correctly, each of those levels will build on to one another so that you're getting further and further down into that paradigm of the really exciting promises of digital twin without maybe wasting money on a boondoggle. So what does it look like to go from 0 to 1? Now, we did this project here in the state with Iliamna New Haven Non-Dalton Electric Cooperative. George Hornberger's the general manager out there. Absolutely love George. Super long time resident of New Haven. Super well trusted. Everybody loves him. He loves his community. And so what he really wanted to do was leave his electric cooperative and his community in a better spot, better than he found it. And so the situation that he came to us with was that they had very outdated documentation. So they have system maps, those big rollout system maps were from the 90s, which maybe isn't that old to some of you, but is pretty old when entire subdivisions aren't even represented. Many of the drawings weren't even correct anymore. And so it's confusing not to necessarily know if what you were looking at is accurate or not. And also, obviously, I mentioned before, they have this logistical issue of having a remote operating environment. There's a few things along these lines, but travel's super expensive. Shipping is super expensive. But also due to their small population, they don't necessarily have all of the technical expertise just down the road whenever they need to respond to a problem. So they're often bringing in outside contractors to work on things that are outside of that day-to-day. And so a lot goes into that, and a lot needs to be considered when trying to cut down on wasted travel, cut down on rework, and really make that an efficient process. And then the last thing I'll say is that they're expecting some workforce turnover. Essentially, George is planning to retire soon. And so all this information that he's built up about his cooperative, it was important to get that documented. It was super important that didn't go with him when he retired. And so you might look at these conditions. You might look at INN Electric and say, that doesn't sound to me like a digital twin a problem, like a problem that needs a digital twin solution. And what I would say is, let's look at level 1 digital twin. Let's go from 0 to 1. So what did we do for them? We mapped out their entire distribution system across the 3 communities and their hydro plant. And then what I mean by mapped out is really just get a low-level understanding of every single asset. So where is every single distribution asset? What are its properties? How many volts? What's the voltage of every single line? Let's understand the phase changes. Let's bring together drone imagery, along with laser scans. Let's pull all these together to have an accurate sort of visual twin, to use that term again, that's spatially accurate, that's photorealistic of all of our assets, every physical asset, every expensive thing that we care about. I want to understand where it is. I want to understand what it is. I want to understand how it interconnects with the rest of my system. And when you start to pull this different information together, you start to unlock a lot of operational efficiencies. You offer a platform for their human experts to put what they know about the system, to track these things, to make these things searchable, configurable, and essentially allow for this collaboration within their team. And so what do they get out of this then? They're saving about half of the trips that they would otherwise take. Or, like I say, bring in contractors out, because now you can just say we're having this issue with the cabinet, maybe that this engineering firm put together for us. They can just take a look at it remotely and save a trip. Essentially, walk an on-site technician through what needs to be done, or do whatever reconnaissance they need to do from a distance. They're finding that they can get to the information they need about their physical assets about 10 times faster. Again, if you just say, I know I need to know about that valve, I'll just go click on the valve, rather than like, what was its asset ID again? Like which filing cabinet is that in? I don't know. I'll go find it, et cetera, et cetera. And so in terms of return on investment, we're just talking about level 1 digital twin here. We're just talking about getting an accurate understanding of their system. And if they can save a single trip out to remote Alaska, they're paying for a year's worth of what this costs them. And so really quickly, you can see the return on investment starting to build on itself and set them up for where they could go next. And this is really what I want to talk through now. They are seeing a return on investment. They have solved all those problems that they came to us with simply with a level 1 digital twin. And so how does that set them up then for moving more into what you might see on LinkedIn that is a digital twin? And so my argument is, now that they have that comprehensive asset management or asset inventory, they're able to say, where should we actually focus our efforts in terms of what to track? What data should we prioritize when we say, let's buy some sensors, let's pull together an IoT strategy. Let's move toward trending. Let's have a historian. Now they know what they need to care about. They know the vulnerabilities in their system much more comprehensively, and they can build a strategy around what data they want to track. I think when you jump too quickly into level 2 and forget, maybe the system level documentation, forget the visuals, you can have kind of a scattered data strategy. And I've seen this happen before, where you just start pulling in data. And you're not really prepared to do anything with the data. And so if you have, again, this combination of visuals and data, I really think that puts you in a great spot as an organization to move into building AI models, leveraging preventative maintenance strategies, leveraging these different things that really allow you to go further, to go beyond just human collaboration, human expertise, and to automate things, to bring out insights that you can't get to just by looking at it as a human, even if you have a ton of experience. And so the argument here, again, to sort of harp on this, is that I think that there are levels of digital twin. I think that all of this falls in the bucket of what you would consider digital twin, and that starting small, starting at something that's accessible, and seeing that return on investment as you go, and allowing that to solve problems that you're already dealing with, rather than just jumping into a whole new world because we need to paradigm shift. I think that this is the way we're going to actually step closer and closer to that full level 3 example of digital twin in a way that's more feasible. That's my argument. That's what I think organizations should do. And I think it'll better empower especially the smaller operators that don't have these huge operating budgets, but can start small and start to see that return on investment, start to leverage these cool new technologies that are getting cheaper and cheaper, and to pull them into their own operations plans and strategic planning going forward, so that they don't have to make the decision between, here's our budget that we were thinking of put into all this deferred maintenance, but I guess we'll bet big and we'll gamble on this big AI thing. Like, my argument is, don't do it that way. Leverage that budget that you've put towards deferred maintenance and start to solve those problems with these technologies rather than seeing them as in competition for the same budget. Would love to take questions. I know that was a lot. I know I flew through here, but I think we've got some time. And yeah, would love to talk more. Thanks.
Wow, great presentation. Thank you so much, Jay. Very fascinating. You answered a lot of my questions right at the outset of like, where does someone even start with considerations? So I liked how you walked us through that. We've already gotten a few questions this morning regarding how to best put this, hallucinations versus reality. So as you're doing these digital twins and you're using data to make these decisions remotely, what are your approaches? How are you going about it to make sure that the information that is being received in the digital twin is accurate and may not just be a result of AI making interpretations?
Yeah. I mean, I think I've heard the term garbage in, garbage out, which I think is a really good way of thinking about this. Is very true way of thinking about this. And I think when you want to apply, AI strategy, machine learning strategy, or whatever to your own specific use case, it's going to take historical data. You simply have to have, a broad base of accurate historical data, and really the only way to fine tune that is over time to be able to identify, this is what it looks like when we have this meter drift, and here's how we can set this threshold and say those data points don't make any sense. Let's cut those out, et cetera, et cetera. Without the trending, without the historical data, there probably are machine learning based, AI based models for cleaning up that data. But I think that's a harder problem than just going through and having that human expert come in and say, those values don't make any sense. What's going on there? And start to really fine tune the data that you are keeping, that you're saying, this is good data. We know it's good. It makes sense. It's accurate. It's accurate with what we were seeing in the real world at the time, and make that the basis for the models that you're building off of. I do think there's a human element there, at least for now. Like I say, maybe there are strategies coming well, you can apply AI to even the cleaning of the data so that your future AI can have a better understanding and use cleaner data, et cetera, et cetera. But I think there is a human element there most of the time that I see.
So, assets evolve over time. You make repairs, you have additions. What does that process look like? Once the model is built, how do you then work with it to make sure it stays up to date and accurate?
Yeah, great question. Great question. I think a few things to say here. When you're using reality capture to build out your dimensionally accurate photorealistic version of what you're working on, I think what's exciting here is that a lot of that technology is getting cheaper and cheaper. It's getting more easy to use. There are drones now that are being flown using AI models, right? So that you just press the button. I've seen people who have never flown a drone before, press some buttons and it flies in and around a substation between the wires, and it's getting these different pictures. If you had to do that manually, you would probably crash your drone. So the idea here being that these new tools allow you essentially to democratize a lot of this reality capture that's going into and is the basis of your 3D understanding of your environment. And so what I would say is let's push out that type work to the everyday people, or maybe even to experts that are out in the community already, sort of adding this as a piece to the economy that, hey, we just built a new addition to the power plant that you had imaged 2 years ago. We need a new scan. What we would say is, that camera is actually not that expensive now. We would love it if, maybe an on-site guy could get that new scan, and then essentially just pass around these exchange formats, a common 3D model format that could be ingested into whatever digital twin system that you're using. I would love to see more and more people doing this kind of scanning, because it is getting easier, and it's a super useful, I think, skill set to have at this point. That's how you would update things is by democratizing it. Crew sourcing is another term I've heard for this, which I think is kind of a cool concept.
Crew sourcing?
Yeah, crew sourcing, essentially saying, while you're out there working on it, could you also just use your phone to, capture a nerf or a Gaussian splat, or use the LiDAR scanner on your iPad or whatever, and essentially have, while not a super accurate version, at least some 3D representation of the thing you went and just worked on. And for that to start to be the input to a broader sort of visual representation of all of your assets, to leverage the people that are already on the ground, to be able to build that out, rather than needing to pull in, bring in the experts kind of thing. I think, crew sourcing would be the way of thinking of that.
So that kind of leads me into my next question. We've heard a bit about workforce development and what future workforce skill sets are needed. So what do we need to do and put in place, and what should leaders look for in terms of their future workforce as more of these tools become more normalized and used in the workplace?
Sure. Yeah, I think an openness to new things is necessary, but I also think there's a way of doing it where you essentially find that balance between respecting and leveraging the knowledge that the older folks have built up over their time of doing it the old way, and try to integrate that into the new way. I've seen really good examples of, essentially saying, hey, we're moving our maintenance strategy in this direction. We're going to modernize our maintenance. We're going to use these new cool tech tools. And this young guy we just hired on, he knows how all this works. So he's, we're going to allow him essentially to take point on this and lead maybe this crew sourcing of new 3D data. But at the exact same time, we're also leveraging the knowledge of the physical assets that all of our older guys have. And that knowledge stream is actually going in the other direction, allowing the new guy who's good with the tech, but maybe doesn't have as much of an understanding with the physical assets, for that to be kind of a two-way knowledge transfer throughout the process of modernizing their maintenance. Because really, in the end, if your digital twin doesn't capture all of that human-grown, sort of human-experienced knowledge base, then I think it's missing out on a lot of what it is you should be documenting. What it is you should be institutionalizing for the next folks that are going to come and grab that role to step into. It has to be two-way.
So as we're talking about documentation and mapping these assets, many of these assets that you're talking about, the physical assets, are some sort of aspects of critical infrastructure. So again, going back to the question of data privacy, data security, and access, what are some things that businesses need to take into consideration of putting in place to make sure that that information is protected and doesn't come under threat, or minimize the opportunities for threat and risk?
Sure. I do think there's kind of often this tension between accessibility, shareability, sort of just an openness and maybe a good-naturedness toward data. And also the flip side of that being, we can't share everything we gather. Obviously, there's a security risk here. We can't just, hey, everybody, we captured the inside of the power plant, everybody just get in there and check it out. Including people that might want to do harm to the system, right? And so yes, of course, there is this tension here. And what I would say is that for the smaller organizations, it's often an afterthought, because they don't have an on-staff cybersecurity expert, right? So what I would say there is I think they would need to leverage vendors to essentially hold them accountable and say, this vendor that I'm bringing in to manage my data, maybe even host my data, I need to ask these questions of them and make sure they have a security data sheet that I can review. Maybe they're even SOC 2 compliant, right? Start to put these thresholds or these requirements in place, even as a small organization, to take more ownership over your data. Even when it's not feasible for you yourself to set up those structures. Does that make sense?
Yeah, absolutely. I'm not seeing any other questions come in. If you all have questions, please put them in the chat. that I'm running out now. Is there any other things that you would want business leaders to consider as they talk about opportunities such as AI? Maybe limited to 3D or digital twins, maybe not. What are some things they have to put in place even to take advantage of opportunities such as this, as using AI as a tool?
Yeah. Great question. What I would say there is really, I think it's very difficult. Yeah, to use my catchy phrase, you can't manage what you can't see. And so to kind of broaden that out, really, you can't manage what you don't know you have. And so the situation where you're just going day to day, you have your day job, you're just trying to keep the lights on. There's a lot of the documentation pieces that fall to the wayside, and you don't really have a full understanding of your system down to the component level. And so what I would say is a really, really useful first step is to have an asset inventory done, essentially to say, here's what we have, here's how it's connected, here's roughly from a high level how it's working together. Because from that standpoint, then you could say, you know what, a visual twin of this component would be super useful for these reasons, or, tracking this data in order to cut down on the maintenance tasks for this system, that would be super useful. I did like what Richard had to say in the previous panel, really of separating this out into specific use cases and treating these things as individual opportunities for tools. And I think when you have an understanding of your system, you've done a vulnerability assessment, that's where you're better able to say, I know we need help in this area, rather than sort of a broader, like, we need help, we're not really sure, and so I think there's a lot can be done, even within, your normal operating budget, to get up to speed on your documentation and sort of have that as a presentation to a vendor that you might approach for a digital twin strategy or for an AI strategy, and say, here's what we're offering you first, rather than needing to bring someone in to build that for you before they can even move on.
Great. Thank you so much for this presentation. It was really interesting, and look forward to seeing these opportunities develop as we move forward into the future. So I understand what you're saying about betting, and it's not a gamble. I agree with that sentiment. Maybe next time we'll put more thought into titling the theme of the event. But I think what you're sharing is truly understanding the opportunities for emerging tech in the future, I think is what we're hoping to share with Alaskans today. So thank you so much for getting us started today. We are going to move to our next panel. So we're going to be joined for our final panel today. We have Laurent Nassif joining us. And Laurent is going to be talking about hydrogen deployments and blending. Please continue to submit your questions into the chat box. And Laurent, if you don't mind taking a moment to introduce yourself and go on with your presentation. Thank you so much for being here today, and look forward to the presentation.
First introduction, my name is Laurent Nassif. I work with ACEP and the Energy Transition Initiatives group. So first of all, a big shout out to this group and all the research that they're doing and trying to bringing up solutions for Alaska. My background is a mix of technical background in engineering, some MBA, so that's the financial part of it, and a lot of project management and portfolio management. So in everything that I present, I always see all those different aspects when I look at a solution. I've been in the energy industry for several decades, but the thing I'm trying to bring in today, that I'm trying to bring into Alaska and to ACEP and UAF, is really my more recent experience, both in Hawaii with projects and assets, which I think are solutions that could be interesting for Alaska as it relates to the energy transition, and also some asset and project experience that I have for my own company where I develop this type of projects. So I'm trying to bring all of that together to support developing solutions for Alaska. I am located in Hawaii. I'm actually inside today. It's very dangerous out there, falling coconuts and the sun and all the noise, with waves crashing. So anyway, that's why I am inside today. And I'd like to talk about hydrogen deployment and blending. I'm going to spend a little bit of time on that first slide because I think it's important to set up the background, some key definitions and key elements as it relates to hydrogen. And first, I want to talk about relevant properties. I know a lot of people have presentation on hydrogen, and they always quote different type of factoids about hydrogen, like how it's the element that is the most present in the universe and this type of thing. But I try to take the key elements that actually will be important for what we're going to discuss now, which is implementable solutions for Alaska. The first one is that hydrogen is a small molecule, and this matters because that's what triggered in the scientific community questions around whether there will be more leaks related to the use of hydrogen through cracks or through joints in pipelines, for instance, and whether a small molecule like that could go in between the matrix of material and create embrittlement and this type of challenges. It has a very high energy per mass, which means it's a very good solution for energy, but it has also a lower energy per volume or lower BTU than natural gas or methane, for instance. So typically you're talking about around half the BTU content. And that matters because that means that all natural gas or methane solutions are most likely applicable for hydrogen, but they will cost you twice the amount. One of the key aspects of hydrogen, be it the element hydrogen or the molecule H2, is that it doesn't have any carbon. Therefore, when you combust it, it doesn't generate any kind of CO2 greenhouse gas. It blends very nicely with natural gas, and there is a lot of synergies with all the natural gas infrastructures, be it transport and distribution, like pipeline. A lot of the generation assets are flexible to produce either or a blend of them. And a lot of the end use, like residential equipment or even commercial equipment, are amenable to blends of hydrogen up to 100% hydrogen. And we'll look at that in more detail in a few minutes, but it also have multiple known carriers, which are typically liquid carriers. We'll go through that in a second. Really, it's seen as a very, very good solution for a long-term and large-scale storage and to convert some of the variable energy solutions, such as wind and solar, into firm energy or firm power at large scale. It doesn't have any smell. It doesn't have any visible flame. And the flame is different characteristics. So that's something to think about when you do blends or when you use 100% hydrogen, especially for residential use, but also for any type of use. So you have the need for an odorant, you have a need for a flaming agent, and you have to tune your equipment to adjust the flame characteristics. But again, all of the solutions exist, and we'll look into it. Some of these are already applied right now in the US. So when I talk about hydrogen, of course, I'm going to talk about the molecule H2, but I also talk about hydrogen carriers. So the three main carriers are RNG, renewable natural gas, actually renewable methane, which has one carbon for 4 hydrogen. And it has a very low greenhouse gas footprint when combusted, at least lower than other type of energy molecules, because it only has one carbon. And of course, there is a lot of synergies between hydrogen, H2, and CH4. And as I mentioned earlier, we can reuse all of this infrastructure. So it's seen as an affordable carrier that is obviously feasible because it's been used for a long time. And it provides a lot of flexibility with different solutions that are existing and these blending components. The other two, which are liquid carriers, are ammonia NH3 and methanol CH2OH. Ammonia has one N for free H, methanol has one C1O for free H. The big advantage of these is that they either don't have a carbon or have only one carbon, so they have generally a low greenhouse gas impact. And they're multi-purpose components. So ammonia can be used as a fertilizer. Methanol can be used as a chemical or as a marine fuel, for instance. And these, because they're in liquid form, it makes it affordable to transport and store, at least more affordable than gases. They're feasible, but typically you would need a larger scale for them to make sense from a financial viability standpoint. Before I move on to hydrogen, I want to talk about some relevant objectives and definitions. So we are all in the same frame of reference. When we use the term renewable in front of hydrogen or any type of end product, for instance, we refer to the sourcing of the process that created that end product. So renewable hydrogen means hydrogen that was generating using renewable sources, independently of what that process may look like. When we talk about sustainable hydrogen, we typically will cover any of the three pillars of sustainability. So it could be renewable hydrogen, it could be related to greenhouse gas, so a process that has low greenhouse gas footprint or reduces or offset greenhouse gas emissions, or a process that protects the environment by reducing pollution and reducing waste. When we talk about zero emission, we typically talk about that for vehicles, and they're not exactly zero emission, but we really focus on one part of the full process, which is the vehicle itself. So hydrogen is considered zero emission. An hydrogen vehicle is considered a zero emission vehicle, for instance. I wanted to talk about also synthetic gas versus natural gas. Natural gas typically means a gas that is generated naturally, that you can find in nature. But in the industry, we use natural gas really to talk about a gas blend that has a majority of methane in it. And that's opposed to synthetic gas, which is a gas that is being synthesized. But oftentimes, when we talk about synthetic gas, we talk about a gas blend that has other components in high proportion. And in one of the cases that I'm going to cover today, when we talk about synthetic gas, we're actually talking about a blend of hydrogen and carbon dioxide. Finally, hydrogen blend means any blend of gases that has hydrogen in it. But in practice, you would have to have, let's say, around 5% of hydrogen or more, to start talking about hydrogen blending. Before I move on from that topic, I really wanted to talk about being cautious about the use of colors and the use of the term decarbonization. I know a lot of people are using colors to try to describe sustainability attributes of products such as hydrogen, but there is two challenges that you have to be aware of. The first one is that we're mixing different type of topics. So the blue color is associated with carbon capture, which is related to greenhouse gas. the green color is associated with a renewable attribute, which is linked to sourcing. And of course, it's difficult to figure out what level of carbon capture do you need to have to be blue or several different shades of blue. How many renewable sources do you need to have to be green or certain shades of green, and then you can have all the different type of colors in between. So I always caution about the use of colors and be very specific about the sustainability goal that you're trying to achieve. The second term is decarbonization. And I'm not going to prevent people from using decarbonization, but D can mean eliminate, or it can mean decrease. And then carbon can mean the element carbon, or it can mean carbon dioxide as a proxy for greenhouse gas. So be aware that that word can mean eliminating any type of carbon, which means also eliminating us because we're based off carbon, or decreasing greenhouse gas to fight climate change, and anything in between. So always keep that in mind when you use that term, and put a definition of what you mean by decarbonization. Okay, before I move from that one slide, and I promise the other slides will be faster, I wanted to reiterate why we're thinking about hydrogen as a solution for the energy transition. The main reason is sustainability. Most of the hydrogen process, if done right, will address all three pillars of sustainability. They will address the greenhouse gas footprint to fight climate change, the renewable sourcing to address sustainable development, and protect the environment by reducing waste and reducing pollution. We also think about the benefits of hydrogen with respect to affordability. Obviously, we live in states where the price of energy and the cost of living is very high. And if applied in the right way, hydrogen is an energy solution that can reduce the cost of energy and enable other type of energy sources or solutions that can also provide those advantages. Finally, we think about the benefits of reliability and resiliency. When you look at hydrogen, think about local solutions, and think about solutions to storage, transport, and distribution of energy across the states. Things that will make the community more resilient and increase the reliability of communities, both in a large city, in the rail belt, but also in more remote communities across the state. Okay, I made it through that first slides. I promise I'll go faster for the next ones. I wanted to talk about, give you an overview of a full pathway for hydrogen, because I think it is important that when we quote numbers, oftentimes cost, we need to look to see if all the elements of the process have been included, or if we're only quoting a portion of it. And there is 5 categories as part of the process: the sourcing, the generation, the storage, transmission and distribution, and then the end-use application and or the conversion. And sometimes the generation will be right after transport and distribution and before the end-use application. Sometimes the conversion will be in between storage, transmission, and distribution. Sometimes the storage can be done using transmission and distribution, like pipeline, for instance, or you may not even have storage in the entire pathway. So you don't have to have all of these and have them in this order, but you want to make sure that you've looked at all the different components of the full pathway. When you look at costs, you want to have an all-in cost, meaning you want to include the cost of each of these different part of the pathway. When you look at reliability, you want to assess the reliability of the entire process, which means all the elements in the full pathway. When you look at sustainability, such as greenhouse gas or environment, you want to assess from cradle to grave, meaning the full pathway greenhouse gas footprint. But obviously, as we mentioned, if you're looking at the renewable attribute, that applies only to the source of the process and whether they are renewable or not. So what are the different ways of generating hydrogen? The three main ones that we're going to cover today are going to be electrolysis, reforming, and gasification. But there's more than that. Electrolysis is basically using water and power to generate hydrogen and oxygen. It's basically breaking down H2O into H2 and O2. Reforming is using typically water for steam reforming with a source of hydrocarbon, breaking down this carbon hydrogen chain to generate hydrogen and CO2. Gasification is the use of feedstock, typically a biomass or waste feedstock, with application of energy, such as power, pressure in the control environment, to break these down to generate certain levels of hydrogen and methane that are varying amounts. Actually, gasification typically produces hydrogen and carbon dioxide, which we often add to that ancillary equipment to generate more methane. But we can also use digestion. A lot of research is going on into using digestion because the bugs that we use for the anaerobic digestion naturally produce hydrogen. So you could change that component, or you can implement physical solutions to basically extract the hydrogen when it's generated. And then any type of separation processes can be used as well to separate hydrogen typically from methane. You can also have extraction of hydrogen. Any type of ancillary refining processes generate hydrogen, and so on and so forth. This is not an exhaustive list. But again, the three main ones are electrolysis, reforming, and gasification. And these can be associated with the creation of liquid hydrogen carriers, such as ammonia and methanol. The ammonia synthesis typically use the hydrogen, mix it with nitrogen to create the liquid NH3. Methanol synthesis typically use hydrogen with the CO2 to create the liquid CH3OH and some water. And you also have hydrogenation processes, which will use the hydrogen to generate liquid biofuels such as renewable diesel and sustainable aviation fuel. This slide summarizes the different type of sources, the main type of generation, and all the different type of application. Today we'll talk about in our case study reforming, so I'm not going to go through that. One of the key elements that I'm developing and that I personally love is gasification, but I won't go through that into detail. This will be the subject of other type of presentation and research. So we'll be focusing right now on the electrolysis using variable resources such as wind power or solar power, and either for gas blending application or for conversion to energy, either through fuel cell or cogeneration. So talking about electrolysis, what type of assets are in operation right now in the United States? So I picked three examples, which I think are interesting with respect to implementation in Alaska. The first one, which is on my left, was developed by New Jersey Natural Gas and is in New Jersey, and I believe it was the first demonstration asset in the U.S. It's a small system. I believe it's 300 to 500 kilowatt system that has its own generation. I believe it has some storage, some small level of storage, and was used basically for hydrogen blending. These smaller assets were really there to demonstrate the safe generation and implementation of hydrogen as a solution. But obviously, when looking at a larger system, you cannot use much of the data that is being generated. An improvement from that asset is on my right, which is the one that is developing SoCalGas and is actually operating in the SoCalGas site in Los Angeles. So what's interesting about that small system is that not only you have hydrogen generation, but you also have a storage tank, you also have a fuel cell, and you have hydrogen blending. So all different type of key applications are in that demonstration plant. They also built a small house connected to it, so you can use the energy from the hydrogen or generated from the hydrogen to power the home, the lights, cook, and so on and so forth. So that's a pretty neat demonstration plant that has absolutely all of those different key components in it. The one in the middle, I think, is the one that is the most interesting in my view. This is a 1 megawatt system that is in Minneapolis, that is owned and operated by CenterPoint Energy. Again, they're generating hydrogen, they're storing hydrogen, and they are blending the hydrogen. What I like about that system is that it's a 1 megawatt, and that can be used to not only solve some solutions for small remote grids in Alaska, for instance, for which 1 megawatt is a perfect size, but it also can be used, provide some very important information when you look at scaling up the process, maybe for a 3 megawatt or a 5 megawatt system, let's say in the rail belt, for instance. So this provides you more information, but obviously the cost is higher. So these give you a little bit of an idea of the type of assets for electrolysis that are available in the United States. Obviously, there is more than that, and there is more assets, including in country like Australia, which will be, I think, talked about at the ACEP. So I wanted to spend a little bit of time back in Hawaii on the Hawaii case study with respect to hydrogen, talking about generation, transmission, distribution, and applications. The two images that are not the Ko'olau Mountains are related to hydrogen generation. The one at the bottom, which is in black and white, was generation of town gas, which has 50% hydrogen, and injection in the transmission and distribution network, which actually was more a distribution network at the time in the early 1900s. And some of those pipes are still in operation. The image on my top right is the synthetic natural gas plant, which started in December 1974, which produces 15% of hydrogen in the blend, and has been used by a resident of Oahu since 1975, so for nearly 50 years. A little bit about that process. I will not go through the detailed process flow diagram that is on my right. but the general idea is that it uses recycled water for steam and a byproduct or waste of the refinery called naphtha to generate the synthetic natural gas, which is composed mainly of methane with up to 15% hydrogen. And there is a CO2 capture element into it. Steam reforming is a technology that is widespread, that is used in a lot of different places. They all have very similar schematic. There's just a difference in the number of phases, where the CO2 stream comes in, and where the different streams, comes in and are recycled in the process. But they all use the same three main set of equations. First, we remove the sulfur from the feedstock, and that's done by hydrogenation and then catalytic adsorption. So we basically mix the SH components with hydrogen to create H2S, and then we absorb the H2S with typically a zinc oxide catalyst to remove sulfur from the feedstock. You generally have, obviously, steam reforming step, which is generally catalytic. So you have your carbon hydrogen components, can be CH4, can be obviously more complex carbon hydrogen chains. You react that with steam, water to create carbon monoxide and hydrogen. And then you have a step where you either remove the carbon monoxide and the carbon dioxide, or you convert the carbon monoxide and the carbon dioxide into renewable methane. So CO react with water to create CO2. CO and CO2 react with the hydrogen to create CH4 and water. Another interesting asset related to hydrogen in a way is related to the transmission and distribution and its use for hydrogen blending. As mentioned, prior to December 1974, the system saw 50% hydrogen. After December 1974, the system saw 15% hydrogen. So for more than 100 years, Hawaii has been using a gas blend with a high amount of hydrogen, and most likely without knowing that they did. The T&D system in Hawaii goes from the west side to the east side, from Eva, which is in the leeward side, all the way to Hawaii Kai, which is at the beginning of the windward side. The transmission line is typically 16-inch steel line with pressure that varies from 500, 450 psi all the way down to 300, 350 psi, wherever you are, depending on where you are in the system. You also have supply lines and distribution lines, which are 150, 30 psi, all the way down to 14 psi, and which are a mix of both steel and HDPE polymer material. So this system, this transmission distribution system, has been used for a very long time to transmit and distribute blends with high level of hydrogen. And of course, a lot of data have been collected with respect to these assets related to, is there any kind of embrittlements? Is there any kind of material issue for all different types of material used in the pipe, but also with the joints, with regulators, meters, any kind of equipment you have in the system? Leak surveys, are there any kind of leak issues related to the use of hydrogen blends, and for all different type of conditions? This blend has been used, as I mentioned, for residential end use without any special equipment related to hydrogen blend. There's just your regular equipment that you can find anywhere else in the mainland. There has been some adjustments on some of those equipments for just to adjust the Wobbe index and to adjust basically the flame appearance. But a part of that, there hasn't been any kind of major adaptation for this blend. And again, it's been used for a long time. I wanted to focus on commercial applications. So use of hydrogen or hydrogen blend for turbine is typically not seen as an issue. A lot of manufacturers have solutions for turbine. Typically, the concern is related to the use of internal combustion engine, for instance, anything that basically will vary pressure. And the concern is related to, will there be any knocking effect? So the photos that I'm showing on the screen are related to internal combustion cogeneration asset in Hawaii, which is in the Sheraton Waikiki, and has been using that hydrogen blend without any issues related to the fact that it's using a hydrogen blend. And discussion with manufacturer, they will tell you that not only they don't see issues with lower hydrogen blends, but they also have solution to retrofit existing system to allow for higher blends, all the way to using 100% hydrogen for cogeneration. So I will skip through this slide, but I think that gives you at least a flavor or more color on the hydrogen experience in Hawaii that's been done for a long time. And both on the generation side, transmission distribution side, and the end use side. I put this slide because I wanted to do a little game. And the little game is basically, which state is it, Hawaii or Alaska? So I'll go through a description and then we can discuss which state that corresponds to. On the resiliency side, I'm talking about a wide state that has a majority of the population in a large-ish urban area, and that has multiple remote off-grid areas. And because this is not a contiguous state, it is dependent on import to the state. On the affordability side, we're talking about a high cost of living and a high cost of energy. And electricity is typically more prevalent than gas. On the energy side, the T&D systems are limited, mostly to urban areas. A part of that, you're talking about microgrids. And on those main areas, they can be capacity constrained. And most of them are based mostly on fossil fuel generation. On the sustainability side, transport and energy are the biggest sector for greenhouse gas contribution. The environmental protection is critical. And this is a state that has kind of like a pioneering mentality, trying new solutions and with an all of the above strategy, looking at renewable gas, hydrogen, geothermal, hydroelectric, solar, wind, biodiesel, etc. On the equity side, it's a state where native communities are critical to the state, not only from a cultural standpoint, but for everything. They're involved in all aspects of the state strategy, and there is a priority done, a preference done to local development. So people from Alaska will be like, well, that describes the state of Alaska. Obviously, living in Hawaii, that describes the state of Hawaii. And the point that I'm trying to make here is that Hawaii and Alaska are very similar states from that standpoint, even though they look different or they seem to be different in the first approach, they're actually extremely similar. And that's why a lot of the solutions that have been developed in Alaska, for instance, for microgrids, are very interesting for the state of Hawaii. And solutions that have been developed in the state of Hawaii for hydrogen, for instance, I believe are interesting for the state of Alaska. So very briefly, I'm going to go through the state of energy in Alaska, the challenges, and how the solutions, what solutions may make sense for Alaska. The slide that is on my right, the pie chart, was taken from data in 2021, only looking at power. So it's a little bit dated, but I think, the key elements are still there. What it shows that there is still a very high dependence on fossil fuel for power generation. There is a very strong hydroelectric community and a lot of assets, hydro assets in the state of Alaska. But other type of renewable energy sources are still, in that case, under 3%, so are still need to be developed. If you look a little bit closer at the challenges in Alaska, there is really 5 challenges. The first one is the declining natural gas resources, especially in the rail belt. The fact that some of those resources are located in remote locations. So how do you store this energy? How do you transport this energy to where the demand is? You have a lot of decentralized small-scale community grids. So how do you cater for those more remote small grids? There is an overall need for increased sustainability and renewable sources for energy. And of course, you're contending with higher cost of living, higher cost of energy. But Alaska is very unique. Actually, coming from Hawaii, when I started looking at what renewable sources are available in Alaska, I was just stunned. Alaska pretty much has any kind of renewable sources you can imagine. So I picked all of those different maps to illustrate that. The one on the left, top left, is renewable wind, hydropower, not only what has been developed, but all the potential that could still be developed. Tidal waves is also available in Alaska. Solar is available in part of Alaska. Geothermal is available in Alaska. Wood waste biomass is available in Alaska, and so on and so forth. It's really the land of plenty with respect to all of those different sources. So what is a challenge? Why has the sources not been developed yet? Well, part of the challenge is limited to the limitation with respect to storage and transport. The map on the left is basically all the roads and pipelines that are available across the state. And the map on the right is available railway and future planned railway that will connect Alaska and connect Alaska to neighboring states and provinces in Canada. So how do you leverage the existing transport and distribution infrastructure to transport the energy where it's needed from the sources? And how can you store that energy more cost effectively? So this will be the last slide that I have. And what I try to do is list and put in 4 different buckets all the type of solutions which I believe are interesting and implementable in Alaska, and try to list that, to link that to the list of the key challenges that I mentioned earlier. So I put the solution in 4 different buckets. The first bucket is related to hydrogen, and I'm looking at electrolysis generation in that bucket. And I'm also including blending into that bucket. The second one is the generation and the use of liquid fuels, hydrogen carriers that can be used for transport and energy need. The third one is the conversion of waste or biomass to renewable energy. And this is more particularly linked to gasification. The last one is any other type of local renewable natural gas solutions or hydrogen solutions, and any local solutions that will improve grid management. So if we look at the declining natural gas reserves, the hydrogen, the waste to renewable via gasification, and the local solutions all will help address that. Developing local RNG can replenish the natural gas supply. Any production and blending of hydrogen can help mitigate some of that decline over time. Obviously, the use of hydrogen has to be phased little by little because you have effect of dilution of the BTU content for the blend, as we discussed in the first slide. If we look at leveraging remote resources, the renewable liquid fuels such as ammonia, methanol, or biofuels are all very interesting solutions that can help with the storage of energy, transport and distribution of this energy from the source all the way to where it needs to be used for transport or for energy use. When you look at the issue related to decentralized small-scale community grid, actually all of these solutions are a solution to that challenge, and it will depend on the community and the setting to figure out which of these solutions may be applicable. Finally, if you look at the need to increase sustainability and mitigate higher costs, again, all 4 of these solutions may be used for that purpose to reduce the cost of energy and to increase sustainability. So that was my last slide. In conclusion, what I was trying to convey is that hydrogen is a very interesting solution, and it's part of the solution, part of the tools that we have to address the energy transition. It obviously will depend on the setting, but also more particularly to Alaska, it will depend on what the community wants. The community is at the center of any of these projects, and they need to drive those solutions. They also know better than any of us, really, what makes the most sense for them. So not only community have to be at the center of it, but we also have to adapt those solutions for the community. Try to simplify them, try to simplify the use, especially for remote areas, so they can be used. And of course, that's why I thought the presentation that were provided earlier today, I thought were all very, very interesting, because those are all tools that we have now in our toolbox, and especially as it relates to implementation of solution or implementation of hydrogen solutions in remote areas. So that's all I had for today. And I'm happy to answer any question if you have any. I know I'm the last thing in between you and lunch right now, so.
Thank you so much, Laurent, for that presentation. That was really helpful. Again, to the audience, if you have any questions, please put them in the chat. Laurent, we're in Alaska and even in Hawaii. We are very used to hearing all of these great ideas from other parts of the world. And the question always comes down to, but will it work in Alaska? What are some key considerations that Alaskans should have in regards to hydrogen deployment as it relates to some of our extreme environments?
Yeah, so that's an excellent question, right? So the thing that we always hear is, okay, those are great ideas. Do you have anything tangible? And that's what we try to do, right, with this presentation, show actual, tangible assets, that have been operated in Hawaii or in other places in North America. Obviously, the intent is to show that these can be applicable to Alaska as well. So as it relates to hydrogen blending, for instance, what is very striking to me is that for the main components of the T&D system, the Hawaii system and the Alaska system are very similar. Similar type of material, similar type of diameter, flow conditions, all of those different things, pressure, and so on and so forth. All of the different things are extremely similar. So we know that the Hawaii system is a very good proxy for the Alaska system. Now, it's not an exact match, right? So we're still there's a couple of areas that we have to study, and as you know, it's part of a proposal that we have that we're studying to make sure that we look at all the different elements. So things that we're looking at is using exact material from Alaska for testing. Things like, is there any impact of temperature, for instance, temperature profile on the system? Does it create additional fatigue on the material, and so on and so forth? That being said, in my view, those are typically more minor parameters. So the Hawaii system is going to be very applicable, right, to the Alaska system. Plus, we saw that there was a system in electrolysis system in Minneapolis, right, with hydrogen blending in Minneapolis, which has obviously a lower temperature than Hawaii has, and is a little bit closer to what Alaska is. So the gist of it is most of these are applicable to Alaska. And there is only a few gaps and areas, that we need to address before implementation, and we're working on it.
Do you want to expand a little bit more on some of those gaps of knowledge and what, if Alaska wants to consider any form of hydrogen deployment, whether it's blended or not, what are some key considerations that we have to do ahead of time to make sure that we're ready for whatever project may be pilot or not?
Yeah. So on the technical standpoint, there is some gap, but they're not big. So we mentioned, for the blending, temperature, specific material, potentially joints, those are things that you may want to look at. On the electrolysis side, the temperature effect is one that comes to mind, and the potential use of storage to have more continuous flow of energy, for instance, is one that comes to mind. To me, it's mostly related to non-technical elements. So when you're looking at implementation into more remote areas, first, engagement with the community is really key. As I mentioned, the community has to drive drive the project, and they have the knowledge of their particular grid and energy need. So this is more learning for us, actually, in trying to understand, understand those system. And working with remote communities, you have to think about the stakeholder engagement, the stakeholder impact. You also have to really think about your system in terms of an operating system, operation and maintenance, for instance, right? You need to simplify the system so you reduce failure risk, because changing a piece, can take a long time, can cost money in a remote area. And you also need to think about capacity building. So, which means training, which means course available to get people more familiar with hydrogen in general, but the specific hydrogen system in particular, so they can be operated effectively and optimized. It also means capacity building in terms of laboratory testing and this type of capability, within Alaska, so you don't have to go to other states to get results. So those are the very key consideration in my view. And we always gravitate toward a technical thing because it's something that we control. But I started my career in a nonprofit working in remote villages, and implementing solutions. So to me, it's never a technical challenge. Is really non-technical challenges that you have to address and think about. And so those are the kind of things I think that are right now the barrier to implementation of hydrogen, and that we're working on.
So you mentioned some of the hydrogen training and skill sets that are needed, but you also mentioned that hydrogen is very similar to natural gas. So what are some of the gaps or skill sets that may be relevant to the transition to hydrogen? And what are some of the skill sets that are a little bit more missing that we need to focus on and make sure that we're up to speed on?
Yeah, I think, at a high level, it's all related to the energy transition, right? So having a good understanding of the energy transition and all the different aspects of the energy transition. So there is some technical aspects, which can be, material, for instance, material compatibility and effect on material for the use of hydrogen or hydrogen blends, for instance. It can be also any kind of generation system. So, for instance, electrolysis, gasification, steam reforming, understanding more in depth those generation systems. Anything related to the end use, for instance. So we talk about fuel cell and cogeneration, for instance, for power production. So an intimate technical knowledge around those system is very important, and anything related to safety, technical safety. So I mentioned the odorant, I mentioned the flaming agents, the nozzles to spread, the flame, and so on and so forth. So there's a gamut of technical, which are more scientific in nature, and some that are more practical asset related training in nature. But to me, it goes beyond just a technical learning. It's also understanding the sustainability aspect. How do you model greenhouse gas, right? And the greenhouse gas footprint. How do you monitor impact to the environment? How do you look at renewable resources? So the sustainability aspect is key. And I mentioned in my background, I have this background around finance. So the financial impact and affordability impact are really key to any kind of these solutions. So looking at it from an economic lens, right? Can I reduce the all-in cost of energy for the communities, for the customers? Because if you don't, it can be a very nice asset, but if it's more expensive or it's not cheaper, then why are you doing this, right? And so that economic impact is also very key. And I would add to that a last element, a last layer of stakeholder and equity. Those solutions are not built in isolation, right? And the purpose of these is not to build something that is pretty, right? The purpose of this is to build something that helps the communities, that the community see value in. So understanding these cultural aspect, understanding the stakeholder aspect, understanding the equity aspect of this is actually critical to any kind of solution implementation. So I think obviously in our team we're looking at technical lectures and training right now, but we're also trying to look at more broader, higher level course as well, so we can touch upon all of those different elements, because those are more, in my view, more even critical than technical subjects.
We do have a question in the chat here going on greenhouse gas, but before I go to that, I want to lead up with one of the comments that you made regarding the BTU value, and you were just talking about the economics. Earlier on in your presentation, you said that due to the BTU value, it costs twice as much to use hydrogen in some cases. So as we're looking at the cost of energy being one of the challenges for everyone in Alaska and Hawaii for that matter, where's that balance, and when can we say that hydrogen is the economic choice to move forward? How does that disparity of double the cost of BTU value relate to energy costs for Alaska in a beneficial way?
Yeah, so there's two different categories, buckets, related to the BTU content. The first one is if you look at it from a storage standpoint. You can reuse most of the solution for storage of natural gas. So that's really encouraging, because there is a lot of different ones and they're generally affordable. And even if it's twice more expensive to store hydrogen in the same condition than natural gas, it's generally at a large scale, long term, it's generally 10 times cheaper than batteries, for instance. So it's all relative, right? So I was making that point. So we keep that in mind, that it's a very good storage solution for large scale, long term. It's a little more expensive than natural gas, but it's definitely most likely our cheapest option on that standpoint. Now, the comment on the end use is related to dilution. And the reason why I say that is a lot of people either don't want hydrogen blends, or they want 100% hydrogen. And neither of the solution, in my view, makes sense. The way to look at it is that you will have some energy dilution the more hydrogen you put into your blend. But obviously, if you have declining natural gas reserve, having something to provide energy is better than having nothing, right? But that's why it's important to phase the blending of hydrogen into your system. If you blend it, let's say 15% or no more than 20%, in aggregate, your customer is actually not going to see a difference in the BTU content. It's going to be relatively small compared to the usage of natural gas. And if there is a premium for hydrogen, which we try to avoid, we try to have it be cheaper, right? But even if there is a premium for hydrogen at low amounts, it will not affect basically your all-in price, to the customer. So as long as you do that in phases, little by little, the customer will not see any kind of detrimental impact from the dilution. So that's why you want to be careful. You don't want to go right away for very high percentages, not just from a technical standpoint, but from a financial standpoint. And if you do that in that way, basically you won't have that impact. Does that answer the question?
Yeah, and energy resiliency is a key aspect. So making sure that we're able to not have those disruptions is a key consideration for us here. So going into the question regarding greenhouse gases, I'm just going to read it directly. How much greenhouse gas emissions are we actually reducing by using hydrogen from production to end of use? For example, the emissions from blended hydrogen use and from generation from carbon sources if the greenhouse gas emissions are not sequestered currently, and where is it trending towards? So let me reread that just without the little notes there. How much greenhouse gas emissions are we actually reducing by using hydrogen from production to end of use currently, and where is it trending toward? What is necessary to reduce or eliminate greenhouse gas emissions from a regulatory policy, technology framework, etc.?
Yeah.
Big question.
So, yeah. And I will give you the typical engineering answer, which is it depends. So it really depends on your system, right? And that's why I'm always very careful with generalization with respect to greenhouse gas, because certain process, if done right, can offer you huge amount of carbon offset and greenhouse gas offset. Some, if not done with that in mind, can generate, greenhouse gas and have a greenhouse gas footprint. And that's true for renewable processes. That's true for even fossil fuel processes, right? Fossil fuel systems can be carbon offset too, as well, right? So it really is dependent on the specific process. That being said, hydrogen has a huge advantage, which it doesn't have any carbon in it. And rule of thumb that I developed by looking and modeling all of the systems, and I've developed and modeled a lot of them from a greenhouse gas standpoint, the LCA greenhouse gas standpoint, is that 70 to 80% of the greenhouse gas for the full process comes from the conversion to power, or the use of the gas via combustion for energy. So anything that impact the emission factor of that particular step will have a huge impact on the greenhouse gas. And hydrogen just does that, right? The emission factor of natural gas is around 30, I believe. And then obviously the CO2 emission of hydrogen for combustion is 0. So any dilution any hydrogen that you include in there, will reduce this emission factor by a large amount and will affect the full greenhouse gas. Now, there is a bunch of little caveat to that, right? Because we mentioned dilution, right? So then is there an impact of flow because you need more of the blend compared to a natural gas blend and so on and so forth, right? But if you look at it at a high level, hydrogen affects 70 to 80% of the greenhouse gas by reducing that factor. The other one that it uses is related to renewable sources. The reason why a lot of those renewable sources are very interesting is because they provide a lot of offset. So I like gasification because the use of waste will provide a very large greenhouse gas offset for the entire system. These waste will go typically to landfills, and in there it would decompose and generate greenhouse gas. So by using the waste in your system, you avoid that emission in the landfill, and so you get an additional greenhouse gas offset by doing that. So it's a complex evaluation, and it depends on the specific system. But rule of thumb, 70 to 80% of your greenhouse gas will come from the conversion of the energy or the combustion, and a large portion of the offset can come from the sourcing. Everything in between. A lot of people talk about transport. A lot of people talk about compression and so on and so forth. Yes, those generate greenhouse gas, but they're very small compared to these other factors.
Great. Thank you so much. We really appreciate your presentation today as we learned a little bit more about hydrogen opportunities for Alaska and hydrogen blending. That brings us to the close of today for our Betting Big. So before closing us out, I do want to provide a quick shout out to Alaska Marine Power. They were hoping to join us in today's conversation regarding hydrogen. They are working on some offshore wind potential and the criticality of proving the feasibility of large-scale hydrogen storage. You can learn more about their project at the Alaska Sustainable Energy Conference. They are going to be participating in the panel titled Diversifying Alaska's Energy Portfolio, Exporting Renewable Energy from the Cook Inlet panel at the conference later this month. So thank you all for joining us for the first day of the Betting Big, Investing in Emerging Energy Technology, sponsored by the University of Alaska Fairbanks and the Alaska Center for Energy and Power. We appreciate all of the incredible presenters, panelists, and of course, all of you, our virtual attendees. Special thanks to Government Event Services for their support in making these workshops a success. We hope everyone learned something today, and please encourage your friends and colleagues to join us again tomorrow, where we'll be diving into the Krafla Magma testbed, the Rural Alaska Experience, and grid forming inverters. We look forward to seeing you all back here tomorrow morning at 8:30 a.m. Alaska time. Thank you so much and have a great evening.